see, it's extremely, numericals, it's extremely hard to ask questions completely new from what I have shown here. And if you're following all these questions easily, if you're making all these calculations quickly, unit conversion, this, that, and all that, you're in very, very good shape. And this list should also help you to revise, make a formula list, and all that. So this list is not available outside. We have got questions from multiple sources. Gate questions are there, friends and links are there, and yeah, it's a lot. So you could also use this for revision. So we are discussing the medical imaging open book paper. Okay, for the first thing, couple of things. So the open book diagnostic. So you had actually time to refer a book, find the appropriate concept theory, answer the questions and all that. He also said it's going to take more than 3 hours. We had about like 3 weeks to complete this. And yeah, so a couple of things. Questions were not specifically of the gate type. Okay, sometimes units were not given, and sometimes relevant data were not given. So the point of this is you'll go refer them, and the process you'll learn better. So that was the intended objective. And so today's class will just primarily test 2 things. I expect everyone to at least understand the questions. Okay. So first thing is recall the correct relation, then apply that relation, use any related formula with proper unit conversions, and get final answer. So we're going to be concerned about these 2 steps. Okay. Whatever we do in the next 2 hours, it's going to be just a practice for this. We'll just look at the medical imaging questions in this particular video. We'll try to complete all the questions. Okay. Quickly, so let's also get the chat active. Okay, let's try to answer as as we are reading the question. Diagnostic X-ray imaging. Following is not a part of primary EM radiation interaction with tissue. Like photoelectric effect, it does interact, and compound scattering, I suppose, is also there. Fat production involves a lot of energy, so this is not a part of EM radiation. And characteristic radiation production also typically is not part of it. This is when there are jumps between electronic shells, right, giving out specific, K to L, M to L transitions. That happens in X-ray production, so not with radiation interaction tissue. Electron with atoms, something with this radiation typically happens. So B and D are correct here. That's a great question. Nuclear
sir,
medical.
Hello, sir.
Yes.
Sir, in Prince and Link has written primary EM radiation interaction has 3: photoelectric effect, Compton, and pair production.
So here, that's what there is one more added diagnostic X-ray imaging. So pair production happens, but for the amount of X-ray exposures involved in diagnostics, pair production, we don't get to this much amount of energy. Okay, the energies are pretty low. Fine.
Okay, sir.
Therapeutic X-rays, yeah, pair production does involve. General EM radiation interaction tissue does involve, but in diagnostics, we don't go to that energy level. Okay? Too high for diagnostics.
Okay, sir.
Yeah, in fact, that's a nice question because this word here is very important. Yeah, even details like this, let's get clarity, right? Let's just not something about the question, also know everything about the question. Nuclear medical imaging, okay. Crystals are used to detect gamma rays. Percentage of gamma rays that will pass through 1 centimeter of crystals. Given half value layer is this. By now, we should be doing this like suddenly someone wakes up from our sleep, we should be able to do these questions. Yeah, so 1 centimeter is roughly 1 by 0.2 is 5 HVLs. So you start with 100%. So we want answers in the percent. So this is 100 into 1 by 2 power 5. Every half value layer decreases by half. So the end of it, it's 1 by 2 power 5. Suppose this is 3.125 rounded off to 1 decimal place, 3.1 is 1. Okay. Yeah, this is some question that we didn't really discuss in class, but I just at the end of the day, just a simple extension of what we did in class. Were you able to follow this particular question? Any of you could quickly explain how to do this?
Sir, I was able to do this, but I had a doubt in this.
Yeah, explain what you did in the doubt.
Oh, so so the formula for this basically the number of incident photons is like we use this basic formula of like n is equal to ni e raised to the power minus mu into x, where ni is the number of incident photons, mu is the linear attenuation coefficient, which is specific for the soft tissue and the blood,
Okay.
and x is basically the distance that the photons have to travel for a particular subsection of the tissue. And so my doubt here was that when we take, let's say, soft tissue, let's say in the equation I put that e raised to power minus mu, which is the for soft tissue, which is 0.4 per centimeter.
Okay.
Why can I not use x as 3, but I have to use it as 1 and 2 twice? Because it's an integral where absorption is happening over the entire course of the tissue.
Yeah, fair question. Simple answer is you're looking at the way intensity changes. Okay, some n enter here, some nd comes out of here. What happens here is non-linear. It's not linear. Okay, you cannot drink coffee by pouring hot water and coffee powder in your mouth and shaking, right? You have to make the coffee in a pot and then drink. So that's a non-linear process. Linear process, you could do that. The relation between n and nd is non-linear. So technically what happens is then this ni becomes, at this junction, it becomes ni e power this difference minus 2 times, what is the
into 0.4.
This tissue, that is 0.4. Okay,
0.4.
minus 2 times 0.4. So this is the intensity we have here. Okay,
and
now
then we
this intensity after it enters the blood interface will attenuate by this much amount. Okay, so now this is a starting intensity that gets attenuated by e power minus whatever attenuation happens in this tissue, that is minus mu times x. For this medium, x is 0.5 and mu for blood, I suppose, is 0.2. Okay, 0.2. And now this is the intensity that we start with here. So what is the intensity that shows up here? So whatever comes in, that gets attenuated. So here at this end, we have take this whole thing. That is what enters here. Then there is attenuation for 1 centimeter. So that will be e power minus distance is 1 times attenuation is 0.4. Okay. So notice this times this is non-linear. So you can't. In fact, 1 second. Let's quickly check if you could add things. Okay. So yeah, you should be actually able to add them because powers of e you could add.
So, but actually the answer changes if I were to directly. I mean, I get the point of how the number of incident photons changes, and hence we have to calculate E separately. And the number of incident photons is only okay like for the initial stage.
So in fact, right now what I have here is all these powers added up 2 into e power 0.4 minus 0.5 into 0.2, so minus 1 into 0.4. So you can technically do that here, right? You could. Why don't you just check that? It should work. Okay. In fact, why don't we make a quick calculation here? So the expression, can we quickly calculate what is e power of that? So in fact, I thought it is nonlinear, but notice it's just powers of u, so we can add this and this together.
So the answer is correct. Yes, we can do this. Yes, you're right.
Yeah. Okay. I suppose so. What we should be getting is, I think 0.05, okay, into 10 power 6. So I suppose this is start with 2 into 10 power 6, and this is e power, let me say omega is correct, should be, I suppose, this. Okay, so this should be 0.55 into 10 power 6. And the units are there in units of ni, it's just number. Okay. So yeah, just numbers. So in fact, in this case, if you do it properly, you could add 2 and 1 together. Relation at the end of the day is linear only. Okay, I thought it's non-linear, but it's linear, so we could do it. And what is going on here is, remember, this is an example of a non-homogeneous medium. The concept we did is essentially the same attenuation, just that happens 3 times, so one after the other. And the actual expression for a non-homogeneous medium, by this non-homogeneous I mean mu right now is a function of x. Okay? Then attenuation over a short distance, very small distance dx, is e power minus mu of x dx. Okay, so attenuation over over a length will be integral of this, and this is attenuation over a short distance, and this will get multiplied by that, so all the powers of e will get added up. So essentially what we will have here is this is starting x value to ending x value, x1 to x2, mu of x dx, and if it is a number, it's n naught. If it's intensity, it's I naught. Then attenuation is this way. In fact, what I have written is I'm doing the integral from 0 to 2. That integral is this times 2 to 2.5, and then I do 2.5 to 3.5. So even if I have essentially applied that formula without saying that I am applying that formula. Okay. So remember, this is how attenuation is defined for non-homogeneous medium. So mu is a function of time, and that's just a simple, because all the powers get added up, it's just at the end of the day e power integral something. Okay. Okay, quickly, this question we have discussed, in class. Most of the questions we should have discussed in class, but just, let's quickly do this. One of you, oh, great, who wants a chance? Okay, so no, all of us answer. So Nandini, can you help us with this? It's a GATE 2020 question.
Yes, sir. Sir, we know the de Broglie property.
Okay.
Lambda is equal to h by t.
Yeah, h over p. And p we have to somehow find from this information. Something acts. Yes, Nandini.
Sir, we know the kinetic energy 1 by mv square is equal to work done qv. So,
fine. So qv, so this is charge of an electron times voltage is v, that is half me, then v square, and notice this is going to be h over mv and mev. Okay, this is velocities, so I'm going to put this is voltage. So yeah, you can find p from this expression, right? Then to find a GATE 2020 question. So one of the things, GATE 2020, 2021 questions, if it is showing up here, I'm not going to do it fully because complete solutions are already available. But nevertheless, we'll quickly discuss this. I notice this is a particle. So we should be starting with the de Broglie relation and not simply do c over f, because it's not a speed of light. And okay, great. Radiographic system. Yeah, see, this is right now, this question looked, those who were in the program knew this question was very easy. Others thought this question is a very hard question. At the end of the day, this is what should happen, right? So e power minus mu1 x1, mu1 x1 should be equal to e power minus mu2 x2. And instead of attenuation, we have mass attenuation coefficients. That is attenuation per attenuation, per density. So we have attenuation coefficient is mu rho, the mass attenuation coefficient is given here, times rho density, and this will be in units of, multiply this, it will be in units of meters. So for this relation, at the end of the day, what we want is just mu1 x1 is mu2 x2. So mu rho1 x1 is mu rho2 x2. Okay, the mu's and rho's are given over here. So this is, we have mu rho1 mu rho2, we have rho1 rho2, and x1 is given. You can find the other. Okay, we have some disturbance from one of you, so this is 0.2. Okay, fine. Quickly, okay, which of the following statements are correct in the context of planar X-ray imaging? Okay, so let's quickly answer. Okay, Samsung, yeah, by now, the questions like this, your ideas are simple. And when things are, slightly confusing, use common sense. You make something fast, somehow the, resolution should become bad. Okay, cameras in photos taken at night look very noisy, right? Some fast X-ray screens will worsen spatial resolution, and then decreasing tube current, lesser the tube intensity of X-rays is proportional to tube current. Decreasing that decreases intensity, so signal is less. Great, and quickly, okay, now this question I want to spend a minute or two. By now we know, okay, so we have photons of this energy, and then detector decide if the photon has not been scattered. Okay. What is supposed to incident is without any scattering, content scattering is contract. With scattering, at least if it is greater than 98, it says it has not been scattered. So what is the maximum angle by which a photon is scattered? Here, there is a thing. Now we can use two relations. Let's do that. Okay, let's quickly time this thing. Can one of you tell me the relation for finding, for finding this? What is the scattered energy? What is the new energy relation?
Scattered energy is equal to.
Okay.
Energy by.
Is it energy? Is it?
E.
Okay, just give me 1 second.
H.
Okay, the incident energy. Okay, why?
By 1 upon.
Okay.
E by m0 c square.
Okay, E by rest mass energy of electron. Okay, and then
into 1 minus cos theta.
So 1 minus cos theta. Okay, now let's quickly do this. Your name ends with, till mega. Try to find theta using the values given here. For those your names, starting with Nandini alphabetically, ending with Swarnendu, I'm going to give a slightly different relation. Okay, so let's try that relation. So we have cos theta is m naught c squared into 1 by e naught, that is, in this case it's ei, okay, minus 1 by es plus 1. So this is the relation between, the constant scattered angle, incident energy, scattered energy. Now, starting with Nandini, try to use this relation and find theta. Others try to use this relation and find theta. Let's see who gets the answer first. Yeah, now of course we calculated this answer back home, but let's just do it right now. I want to illustrate an important point here. Oops, my water bottle is not here. I'm going to starve. So EI is larger, so this number is smaller, so this is slightly negative. This one minus.
I got using the second ones.
Yeah, that is notice. So at this stage, this method is faster. That is, given energies you want to find theta, this is faster. But uh, given theta incident energy, you want to find scatter energy, this is faster. Okay? Faster for this question. The point is this. So it's the same expression rewritten. Nothing then. Just because some formula is there in the book doesn't mean that's the only formula you should remember. Some variant of that will make your life simpler. Okay. So always look for such shortcut simplifications when you do this. In fact, finding this cos theta is actually quite involved. Unfortunately, this energy is on kilo electron volts. We know m naught c square in kilo electron volts. Okay, so we can slightly save some time, but otherwise this is a big mess. So actually you could do this very, very fast. Okay. And so point is, just because some formula is given, don't memorize it, but see what would be convenient. See if there is a form, look for mnemonics, look for alternative forms that will make your life easier, not just for this problem, but general formulas in general, expressions in general, and relation in general, tools in general. Okay. Okay, we don't have a lot of time, so I'm going to quickly go to the next question. Okay, point source radiation exposure at distance d from source follows inverse square. We know this. Exposure at 30 centimeter from a point source is 1 Röntgen. What is the exposure at d? 5 centimeter. Yeah, this should be. This is take this at 5 centimeter. It should be higher, and it should be based on ratio of the square of the ratio of the distances. So it's going to be 30 by 5 square. At this stage, I can do things this fast. So it's going to be 36 minutes. Yeah. Even the units are important. So quickly, let's make sure to remember that. Consider a chest X-ray of 20 kiloelectron volts. Intensity, ignore tissues other than observed dose below 10 millirams. What should be the limit on the exposure? Okay. Find correct values of required mass attenuation coefficients. Yeah, we need mass attenuation coefficients for the lung and for air to find F factor and also the conversion, right? Quickly, how is Röntgen and Reds related? Have I given that?
0.87 radiation.
0.87 rams, right? There's one relation, and F is mu rho of lung by mu rho of air. So what is F? So I suppose mu rho of lung is 0.83. Okay. This is 0.83 by 0.78. Okay. And then, so this value turns out to be 1.064. 1.064. And then our observed dose below 10 rats. Right? So 10 rats corresponds to 10 by 1.064. 0.64 rads in lungs. Okay. So this is quickly, what is this? 9.4. Thanks. So this is 9.4 millirads. Millirads. And if you convert that into rendons, that becomes, yeah, this should be 10.75, yeah, 10.8 milliliters. So just use this conversion over here. So doing it this way, we know what a factor is and where the unit conversions are happening. So, okay. Suppose an acceptable chest radiograph was taken using this. Suppose that now request should be taken at 1.5 instead of this. What MAS setting should be used to yield the same exposure? So it depends on intensity, depends on exposure, tube current and exposure time. So we are just going to change the tube current and we want to keep the exposure or the intensity same. Okay. So from one you could quickly move to the other using the energy of one photon. But here, what is the relation? Quickly, can someone, inverse square law, can you tell me the actual statement? How should these numbers be related?
IR is equal to I0.
Okay.
IR is equal to IS upon 4 pi d square.
4 pi d square. No, but this is not between an exposure at some distances, right?
Sir, MAS mu is equal to MAS old d square mu upon d square old.
Okay. So first thing, let's see, at the end of the day, what we should remember is intensity is proportional to MAS, right? If we keep the exposure time the same, then only change the current. Okay. So MAS old and MAS new should be related by inverse square law. So MAS new should be equal to MAS old, and this times which one should be higher? MAS old is at 1 meter. MAS new at 1.5 meters. Obviously, MAS new should be higher, right? So it's 1.5 by 1 square. So what do we get here? Oh, at 1.5 we need the same exposure, so the current should be higher, right? See, Jiva, I just use some simple logic. That is, at 1.5, if I have to get the same exposure, I need a higher intensity or a higher MAS. So I did 1.5 by 1. Don't do 1 by 1.5. Get the wrong answer. So that is 30 into this square, I suppose 1.5 square. Suppose it's 67.5. Okay. Suppose this chest X-ray is taken at 2 yards. Okay, 14-inch by 17-inch film, assuming no attenuation. The smallest ID or I naught across the film is ratio. Oh, now we have to just compare across the films. Yeah, say there is something at the center. Then we have this, the intensity at the corner will be the least, right? So we have I naught here. I naught will be smallest at the corner. So ID or I naught will be smallest for a corner. So what is this distance? And 2 yards to inch conversion, anyone remember how many 1 yard is?
72 inches.
72 inches. So roughly we have like this is IS by 4 pi 72 square. Okay, this is I naught, right? And we have ID is whatever at the source by 4 pi. What is that distance? Can we quickly find, let me know this distance?
Under root of 14 divided by 14 divided by 2 square plus 17 divided by 2 square.
Okay, so that is 7 square plus this is 8.5 square, right? And that is
11.
how much is it?
11.
Okay, 11 inches. Okay, so this should be 72 square plus 11 square. So that is the total distance. If you look at this triangle, this distance nu r is d square plus d square plus r square. Our r is 70. Okay, and so based on this, what is I naught over id? It's ratio of these two things. Quickly, what is the ratio we get? So our id over I naught will be 72 square by 72 square plus 11 square. Okay, now comes a couple of questions. What are the factors that we should actually account for? I only accounted for one factor. We have to account for one more thing. What is that?
So is it attenuation? But since we're assuming there's no attenuation.
Yeah, I am assuming. I did. So we know there are a couple of factors. There is this inverse square law effect, and then we also have this. This is at an oblique angle, obliquity, right? So at the end of the day, if you look at this is theta. Our cos theta will be r by this hypotenuse, root of r square plus by b square. Okay, and this ratio, this is just based on this is cos square theta. That is just based on inverse square law. We also have to account for obliquity. That has one more constant. So this is, instead of squares, I should have cos cube theta. I had it as cos square theta, but it should be cos cube theta corresponding to one more factor from obliquity. And if you put that, so what is cos theta that we get here? Cos theta, I suppose, is 0.92. 92. We have something slightly different. So 72 square plus 11 square. Okay. Square root of that. 72 divided by 5. So I have 0.988. And cube of that should be cube of that is 0.97. 0.965. So notice, yeah, if there is attenuation, there is one more factor, e power minus newtons. But without that, we have to consider these two. They just say inverse square law, it's cos square. They so don't say anything, consider both these cases. Okay.
So in the last question, can you please tell me the relation that we've used for cos theta? I think I may have used the wrong relation.
Cos theta is just r by this adjacent by hypotenuse, right? Adjacent is r. Hypotenuse is square root of r square plus t square. And d we just calculated 11.
Okay, sir.
And then for this relation, yeah, so yeah, see, at the end of the day, this is a simple explanation. Okay, we'll do that when we deal with the image formation aspect. But quickly, how is this SNR? How is SNR related to all the details given here? Anyone? Can you give that in the chat?
It's C into square root of A, R, T, eta, psi, all of these.
Okay. C comes outside that times, so a product of the rest of the things, right? Okay.
Yes.
Phi, R, T, eta. Okay. So then, this is SNR. You should get this, typically in amplitude. Then you should do 20 log to get us deal. So let's do the calculation. Okay. This should be, let's have things in 1 unit. So this is 0.1 mm square. Let's do that to centimeter square. So that is 0.1 square. This is in centimeter square, right? 0.01. And then efficiency, just a dimensions number. T right now it's okay, fine, do it as such. This is, we have a Röntgen here. This is Röntgen, so this is 50 into 10 power minus 2. Okay. And so just multiply all the things with the same units. So we should have
6.3.
6.3. Just let me also do that. 1 second.
Yes, sir. Sorry.
0.85 into 0.0. Square root of that into 0.1. Yeah, what I get is 6.3. Okay. Now, this is just the ratio of the amplitudes. To get that in decibels, we do 20 log of this. Okay. 20 log, whatever SNR we calculated, this is SNR dB. That is SNR expressed as a decibel. And this is the ratio of amplitudes. Okay, so we need a 20 factor here. So this should be 16, 15.9 or something. So why this happens, this is just a simple thing. What are the factors that kind of decreases the signal? It's pretty much all of these things. Efficiency at the receiver, okay, first the more incident photons, higher signal is, things like that. Okay. So I will explain this when we do image formation. But right now, remember this relation. So the C alone comes outside. Rest of the things just get multiplied. And, okay, let's pick someone. Sulaim. Okay, we got many answers. Which one is correct here? Jagruti. Jagruti is usually silent. Okay. See, at the end of the day, we know, it's pretty simple. Ultrasound speed, we know what it depends on. So it doesn't depend on frequency. Okay. Penetration depth and all that depends on frequency, but here it doesn't depend on frequency. So just like that. Okay. It's 830 nanometer laser Doppler flow. So we have to be slightly careful. This is not sound Doppler, laser Doppler, but still the same things, we can use. Again, the Doppler shift here will be equal to the thing. This is Doppler shift delta F should be supposed to 2V cos theta by C. C is the propagation speed of this whatever wave you are sending. Here we are sending a laser, so this wave is light. Be careful about it. that times the incident wave, right? Here the incident wave is not given, so we have to convert C as lambda times F. So FT gets cancelled, just find this term, should get the Doppler shift. Suppose that is 36.14. Yeah, make sure you do all the units carefully. So V is actually 3 into 10 power minus 2 meter per second. Okay. And then cos theta is cos 60. Then our lambda is 830 into 10 power minus 9 meters. So this is in meter per second, this is in meters. So they will cancel and we'll get more per second. Okay. Okay. So yeah, this question can someone help Prabha or Mishta, can you help? Okay, PCT crystal of this match, how do we solve this? So again, it's the same problem essentially, right? Doppler shift in ultrasound wave for a blood flow of 10 centimeters, wave velocity is this, at an angle is this. So again, it's the same formula, that is, what do you want? Doppler shift. Okay. Doppler shift is 2v cos theta by C into Ft. So interestingly, we are not given Ft or lambda, but we are given this PCT thing. So we know for PCT, the resonance frequency, the thickness should be lambda by 2. That is the speed of the crystal, Ct, by 2f. Okay. So we kind of know Ft from here. So Ft is Ct by 2. Notice we have C here, 150. This is speed of sound. We have speed of sound in PCT, we have speed of sound in soft tissue. So just substitute this F here, we should get the answer. What do we get there? 22.4. Roughly, I suppose 225 hertz. Okay, ultrasound transducer is this. Yeah. So quickly, formulas for axial resolution and amplitude reflection coefficient. It's very, very simple, right? So we have axial resolution is, so 3 cycle long pulse. It's the n lambda pulse length by 2, half of pulse length. Okay. So if it has 1 cycle long, just lambda by 2. If it has 3 cycle long, n lambda is known as pulse length. Known as pulse length. And then this amplitude reflection coefficient is one of the easiest things. This is AR, let's say amplitude reflection coefficient. Z2 means Z1 by Z2 plus Z1. And what is Z? Z is an impedance which is rho C. So rho and C are given over here. Density and speed are given over here. Very, very basic question. But yeah, 0.75, 0.2. Yeah, now, so last question was a GATE 2020 question. This one. This question is a GATE 2021 question. BM 2021. So let's again get the expressions here. You know, at the end of the day, we just need to remember the two things. Oh, one is Snell's law. Okay. Even if you couldn't remember the second relation, first relation is very, very simple. Sin theta 1 by sin theta 2 is C1 by C2. So notice speeds behave inverse to refractive indices. So had it been in terms of refractive indices, it's N1 sin theta 1 is N2 sin theta 2. But here in terms of speed, this is C1 by C2. Okay. And then Yeah, if we use this, you should get the transmitted angle to be 58, and then we have to do the, this is intensity transmission, right? What is intensity transmission formula? Anyone remember that?
For Z1, Z2 cos square theta 1
Square
upon
theta 1
theta
upon
1 upon count Z2 cos theta 1 plus Z1 cos theta 2 whole square.
Z1 cos theta
Theta
2
2
whole square. So these two things are interchanged, right? Yeah, there is this interchange. Why that happens? Of course, we have seen the derivation. The whole square. So yeah, that should give us 0.94. Again, in the case we have enough, we are directly given impedances. So that is one. So remember this and notice we have the only way they can modify this question is one of them I already said. They can ask you for pulse length instead of axial resolution. Amplitude reflection coefficient, they can ask for amplitude transmission coefficient, and or intensity reflection coefficient or intensity transmission coefficient, which is what they asked here. Things can be at an angle or things can be normal. Things are normal in this question. That is, the thetas are 0 degree, and things are at an angle here. We have theta 1 and theta 2. Okay, fine. But a very easy question. So just remember the relations. Suppose a steady state sinusoidal wave frequency is traveling in z direction. Wavelength is. Okay, this is traveling in the liver. It's we are not talking about light. Okay, so we have this is just assume speed to be 1500 and move on. So we have C as lambda f, lambda is C over, and C if it is not given, assume it's 1500 meter per second. Okay, and get the answers in mm. Yeah, it's in mm. One thing, so when mm is given, you can't enter the answer in micro. Okay, so 0.75. So some of you might have used 1540 because it's liver. Yeah, the decimal might slightly change, but you shouldn't entering 750 here is certainly incorrect because we want the answers in mm. On gate, they will always specify what the units are, so you are not left with any ambiguity.
Sir, I have a doubt. 2 questions ago, when we were talking about the axial resolution, there we have the number of cycles to be 3 and the wavelength to be 3 megahertz. So how do we get 0.375 there?
No, we don't have the wavelength to be 3 megahertz. Megahertz is a frequency. So lambda is C over.
Oh, sorry. So sorry. Yes. So sorry.
So we have to do 1500 by 3 into this thing, 10 power 6. So this will be in meters. Okay, meter per second and this per second. So this answer will be in meters, and then convert that into mm. Okay.
Yes, sir.
Okay, ultrasound transducer pointing the z direction. See, at the end of the day, this is a traveling wave front. Okay, some wave is traveling with a speed of 1540 meter per second. Okay, so the leading edge is, of course, the edge of the wave. For it to travel 10 centimeter, how much time will it take? We know the speed, we know the distance, can calculate time. At the end of the day, that is what it is. So these are all distractions. The question is at an analysis synthesis level. Of course, if we understand the wave is going to look like a delayed function of this, that is fine. But it's really a distraction here. All you have to recognize is time is just, speed, distance, time, however they speed is distance by time. So time is distance by speed. Distance is 10 centimeters. So 10 power minus 2 by speed is 1540. Okay, we should get some answer in 10 power minus 6. Yeah, that should be roughly, 65 microseconds. Okay. So be careful about distractions. Okay. So in fact, this question is a much simpler question. It's just directly Snell's law. So we did that GATE 2021 question. Okay, apply Snell's law, then apply, also find the transmission coefficient, transition coefficient. Here just find the transmission angle. Again, Snell's law. So we have sin theta 1, sin theta 2 plus C1 by C2. Are we given C1, C2? No. Yeah, so we'll have to, in this case, we need speeds of things in fat and liver. So we need C fat and C liver. In GATE, they will give these values. Okay, so let me just, for completion's sake, let me write those values. C fat is 1450, C liver is 1370. Okay, so this information for this question should be given. This is 1450, right? 1570
14, 15.
meter per second. So you know this is yeah, first one is C1 is this, C2 is this. You can get the angle that to be, I suppose, what do we get here?
49.9.
Roughly, 50 degrees. If they ask you for 1 decimal, it's 49.9 is the answer. And suppose 5 megahertz is this interface, take both attenuation losses into account, amplitude losses in decimals, if you're returning waveform. Okay, so what we have to do is we have to reuse a couple of details. I'll tell you two things. So loss is a combination of two things. Loss, attenuation plus loss reflection. So at reflection, at an interface, we lose some amplitude. So there is a loss due to that. And there is loss due to attenuation. Can someone help me alpha for this thing? That is how much decibels per centimeter. Can you finish typical value of alpha for the one? Can you quickly look at the book?
20 log into mu a.
No. I don't want that formula. We all know that formula. I'm going to tell you a shortcut, but that I want that constant. What is that alpha in that problem?
20 log into mu a.
20 log into mu a. Again, now we don't want that.
8.47. I'm not sure.
No. There should be decibels per centimeters. Alpha.
8.7 mu a.
Okay, so no. 8.75 is the decibel to Napier conversion. Either tell me that okay, we have alpha. See, alpha is A F B. B is 1. Okay, so either tell me the value of A or tell me the value of alpha.
A is 0.63.
Okay, at least fine. Let's start there. A is 0.63 and also the units. There should be decibels per centimeter. Okay, and per megahertz. Correct? Okay, now, so at the end of the day, so if A is given, B should be 1. Notice if you multiply A and F, you get alpha as, now F is given. Alpha is 0.63. Then is wobbling 0.63 into 5. Notice this is decibel per centimeters. That is, per centimeter of travel, we lose this much. There is loss of this much. That is what this alpha mean. Okay, forget formula, couple of other things. So this is, I think 0.63 into 5. So this is 3.15 decibel per centimeters. So how far away does it travel? So I suppose it's a two-way trip, right? Yeah, things get back. So it travels 4 centimeters. So per centimeter, this much loss. For 4 centimeter, how much loss? For 4 centimeters, loss attenuation, the first component, okay, that is 3.15 into 4. 3.15 into 4. And answer will be in decibels. Okay, what is this? 12.6. Okay, now, so this is, no, we already got a part of the answer. Okay, so for example, if you calculate AZ by A naught or some of the other things, let me also quickly do, just give me 1 second. Into 20. Yeah, if you calculate AZ by A naught, that is use this relation, that will be like 0.234. Okay, and if you do 20 log of that, interestingly you'll get loss is 12.6. Okay, you don't have to do any of that AZ by A naught things. If A or alpha is given, you know the loss per centimeter. This loss is due to attenuation, you know that loss per centimeter, how much ever distance it travels. In this case, it travels back and forth, so 4 centimeters. Multiply that, you should get the attenuation loss. Then, of course, we need the reflection loss. It's also, you know, typically, let's see what the values were over here. We found the intensity coefficient here, right, for this problem. There is this. Gate. Just give me 1 second.
So 1.66 and 1.3.
Yeah, this question. So, what was the amplitude reflection coefficient? That is, what amount of amplitude does it get back? In this case, it's 0.11. So, what is the loss corresponding to 0.11? So that will be 20 log of 0.11. Okay, and so that is the second chunk here. So this number can be slightly different. Is there sufficient info to calculate this loss? Now the question is slightly open-ended. So my the loss due to reflection is 0.11, and this in decibels should be 20 log 0.11. What is that? Into 20. Okay, this corresponds to roughly, you know, it's a loss. So 90 decibel loss. So it's negative. Okay, and this is a loss. This is a loss. So the total loss. So this, notice this corresponds to loss reflection. That is a point of the amplitude reflection coefficient, density reflection coefficient now. Okay, loss reflection. So our total loss is sum of the two losses, 90 plus here what do we have? Some 12 point something, 12.6. What is this? $31.6. And sometimes we have to be careful about the sign of the losses. It's always, you know, they express with the minus sign. There is a convention here. So a decrease is this much. In terms of loss, you say it's, you know, minus 31.6. So we lost this much amount of the amplitude in decibels, and loss is usually negative, expressed as a negative number. So answer you should enter should be minus 31.6 decibels. And notice I got it really, really easy compared to, the thing, because that is the meaning of this alpha. It captures, this loss. Then the reflection factors, using that we can capture this loss. The total loss is sum of these two, usually expressed as a negative number. Okay. Questions here?
So I have a question.
Mm-hmm.
So the returning waveform that is being called over here, it is the reflected wave, right? The wave that is being reflected from the interface.
Mm-hmm.
So then, why are we taking the reflection loss into account? Shouldn't we take transmission loss?
No, that is if Ri is incident. Okay, let's look at again what is this 0.11. So something was incident, that is amplitude incident. Only a part of that got reflected back. And in fact, this is a pressure wave, so this is PR by PA. Okay, so this is a signal we sent. This is a signal that got back. So why are we concerning about the transmitted thing that went away? That's it. It went, then when it hit some other interface, something else. But what we got back is this reflected thing. This is a echo that we get back, right?
Yeah, yes, sir.
Yeah, so at the transducer, we get back this. It gets back at a lesser intensity. We quantify it as a loss. So we are looking at PR.
Okay, yeah. So this ratio we are measuring at the end.
Yeah, notice, so this ratio is known as this, in this case, amplitude reflection coefficient that turned out to be 0.1. So,
Yeah, okay.
and it's ratio of amplitude, so we do 20 log of that. Or in terms of this intensity reflection, is just, square of this number, 0.11 square. So if you use the intensities, you could just do 10 log of the intensity reflection coefficient. Okay. Yeah. So yeah, your question to your answer, the reflected wave is what we are looking at.
Yes.
Okay. Suppose, okay, it's known that 5 MHz transducer makes an angle that is related to direction of pulse, Doppler frequency measured as this. Okay, now, we know the velocity, we know the Doppler frequency. Okay, this is delta F. Okay. Again, another straightforward question here. Jiva. So yeah, before we get to this question, let me also finish. At the end of the day, this loss is expressed in decibels, Jiva. Okay. So now, if you want the answers in Napers, very different unit, you have to do that point, multiplier divide by 8.7. Okay. Answers in attenuation in Napers per centimeter. But we are looking at loss, which is expressed as decibel. So we stick with alpha. We don't go to attenuation coefficient at all. In fact, a good question. Be careful to use alpha in decibel per centimeters to find this attenuation loss. Don't use mu here. Think it a incorrect answer. This is pretty straightforward. I suppose it's. Sir, will be mentioned. So yeah, question will mention this attenuation loss is this much decibels per centimeter, or they will give this A is decibel per centimeter per megahertz. You know what they are referring to. Based on units, you know whether it's Napers or decibels. It will be mentioned in question. And these numbers, yeah, will be given. One of these numbers, either A will be given, you have to presume B is that, or alpha will be given. Or mu A could be given, from which you have to find alpha. One of A, alpha, mu A will be given. Right? How about this 2A cos theta by C into F? We know F, we know theta, we know delta F. Oh, we have to find V. Can we quickly, rearrange things, find things, and as you know, this is Doppler ultrasound, right? 500 hertz. We are talking about blood. So this is C is going to be 1500. I suppose, yeah, many of you have that answer, so I suppose that is correct. 0.08, 0.089 meters, at least 3 decimals. Consider a flat 1 centimeter transducer operating at this bandwidth. Doesn't make sense. There's a typo here. So this is beam width at a range of beam width at 20 centimeter ranges. So I think from yesterday's class, we know what we are referring to. So we start with this. We have a geometric region, and then we have a Fraunhofer far field region, right? So are we here or are we here? So what is this d squared by lambda, the geometric region given this? So d is given. Can you quickly find what is d squared by lambda to determine which region we are in? And yeah, this being recognized, we are talking about ultrasound. So C is 1500. D squared by lambda is, yeah, let's also be careful about the units. It should be 1.5 centimeters. This is less than 20 centimeter. So we are, of course, at the far field region. So we know the beam width is lambda C by D. Had it been less than 1.
D square by lambda is equal to 13.4 centimeter.
13.4 centimeter. So okay, let's just check that. Anyone else quickly? What is d squared by lambda? I could also do that. Oh, we want things. Okay, this is not 1.5. What is d squared by lambda? Someone else? So quickly we have 13.3, 13.4, something like that. So 13.4 centimeters. Simplest will be convert distance centimeters. This is in hertz, so 10 power 6 seconds per second, that will cancel. So just convert this into centimeters, 2 more zeros, and then should calculate this.
Hello, sir.
Yes.
Sir, why C is equal to 1500 meter per second?
Because 2 megahertz, we are referring to ultrasound.
Sir, in water, I think it's 1484 meter per second.
Approximately. If that is not given, yeah, if it is exactly, it is given 1484, take that value. If it is not given, approximately 1500 in water tissue. Okay.
Okay, sir.
Yeah, if I use even, the answers are not going to differ by a lot. You'll be nearby. Okay. So the final answer width, I suppose, is 1.5 centimeters. Okay. And how is, let me also write this relation. Where is lambda? Lambda is just C over F. F is given to be 2 megahertz, and our C is so 1500 into 100 centimeter per second. Fine. Okay, ultrasound transducer based in this thing. Yeah, these are some of the problems we did yesterday, right? Let's quickly do that. Side lobes, this lobe, and all that. The same thing. Again, I suppose our Z is greater than d squared by lambda. So we are working on far field. So you can check dx, dy. What we want is along x-axis. So along x-axis we have dx, and along y-axis we have dy. So just take this, and w is lambda z by d. Just discuss this. A peak of the first side lobe should occur at 1.5 w on either side. Okay, so that quickly, yeah, we just did this problem yesterday. So we know Z. Let me point out things here. So we know dx, which is what we should be using. Then we know speed is given, frequency is given, so we can calculate lambda. And then this is Z. Yeah, and we should be using dx. 1.5. This should be, what do we have? 17.3. Yeah, 17.3. And the side lobe occur at either side. So plus or minus 17.3 centimeters. Great. Now consider transducer, the same speed of sound, won't transducer work at a frequency. Thickness of the crystal should be. In fact, it's a much easier question, right? We already saw that. We can relate thickness of a transducer. That should be, for resonance, it should be lambda by 2. So this is C by 2F. F is given, C is given, CT. So the speed within the transducer, and F transducer is also given, so we can find the thickness. Okay, what do we get? And the thickness in mm, suppose, yeah, it's very, very small, 1.4 mm. We can barely see the thickness. And we have, in fact, this is a 1 mark question. They want to make it a 2 mark, they can mix and match it. Estimate frequency from here, then find the Doppler shift. Okay. Oh, consider a mechanical scanner. Okay. So yeah, this is speed, distance, time, and polar coordinates. We know that time. Okay, the distance is 90-degree window. That is 1/4 of a revolution. So speed is time can be based on maximum depth. Okay. So time is distance by speed. Distance is twice this, 2 times 15 centimeter. Okay, 15 centimeter, because it goes and then gets back. So goes 15 centimeters, gets back 15 centimeters. So twice that. Speed at which it travels is 1540. So find time from here, and then so that should determine the distance is 1/4 of a revolution. So the maximum speed is limited by these two. So speed is distance by time. Suppose they want the speed, right? Yeah, the maximum rate of revolution. So this is not in revolutions. Okay, the maximum rate of revolution should be revolutions per second. Suppose that's a slightly big number, 1,000 or something. What do we have there? Yeah, that the time itself will, if we calculate that, that roughly comes down to, I suppose, 20 or something. There should be approximately 19.5. Is this milli or microseconds? Okay, milliseconds, and this should be, so once you use this time for 1/4 of a revolution, the speed should be 1283, 83, 82, approximately that. Okay. Suppose, okay, nominal gain is this, amplitude gain of the system, just, this is 20, log amplitude gain is 80. So what is amplitude gain? J is 10 power 80 by 20, 10 power 4. But of course, we know how this, we discuss how this is applied in 10 gain computation. That is fine. Linear transducer array is operating at 2 megahertz and the phase of each transducer analysis. Geometric approximation to be valid up to 10 centimeter range. Okay, number of transducers to be good. I already said this, the smaller dimension is what we are concerned about. Okay, so our d square by lambda should be 10 centimeters. So based on that, what is our d? This implies, in fact, I kind of remember from yesterday's class, it's roughly 8.6 mm, right? Yeah, 8.6 mm. Based on that, we can have 9 transducers. At least cover this, we need at least 9, so that it makes our day is combination of all the transducers comes to is at least 8.6. So we need 9 transducers. Ultrasound imaging operating in D mode requiring 256 pulses generate that. Okay, material being images. C A is this. Okay, so yeah, we have to connect a couple of things: penetration depth, decibel loss to penetration depth to frame rate, right? So anyone remember the final relation between things given here?
F is equal to L upon
1 second. So the frame rate, right?
yes.
Okay.
F
F is equal to
L upon
L upon
2AC
2AC.
TR.
What is that?
TR.
Okay, TR. Okay, TR. Fine. Do we know all of this right now? Okay, loss is given. Then what else? There is no N at all here.
256.
And I mean, that doesn't show up in the formula.
So TR is equal to 1 upon F into N for finding TR.
TR is 1 upon F times, yeah. Yeah, let's also think, so this is a small f, okay. Let's write down what is what. So this is N, okay. What is this F? The frame rate. Okay,
Yes,
this
sir.
frame rate is capital F. This working frequency is small f. Okay, loss is given, and we have A is 1. We have speed, C is given. Then yeah, we can get all the things we want. Quickly, what is TR? 1 by Fn. So let's just calculate that.
0.26
0.26 milliseconds. Suppose. Okay, this is 0.26 milliseconds, and then we have other things that. Yeah, because A is in decibel per centimeter, just use laws and decibels. Okay, decibel will get cancelled. Yeah, we discussed this issue. We have to convert one of them into centimeters. So likely we'll have to convert C into centimeter per second, because this is in centimeter per centimeter. This is in meters. We have to do the conversion. So what is the frequency we get here? Megahertz. I think there was a mistake in the book answer. Right? And does this 2 remain here or does it disappear?
So it's disappeared. Sorry.
Yeah, the 2 should disappear by this relation. So quickly, okay, what is, can someone tell me what the final megahertz is? Small f is? I think we just calculated this yesterday. Yeah, it should be 0.02 megahertz. Okay. Princeton link likely says it's like 2 megahertz, but based on the numbers, is what we get. Okay, linear transducer array. This is between the center and that. Yeah, this we discussed 127 transducers. So center transducer, how many in this side? 126 by 2 in this side. That is 63 in this side. So the last transducer is at a distance of 0.8. 0.8 mm is 0.08 centimeters into 63. Okay. This is a last transducer distance. Okay. So focal point at a z-axis of centimeter, 5 centimeter. We assume that to be directly beneath one of these transducers, center transducer. So this is R0. We have R63 here. Okay. So this is 0.08 into 63. This conversion is correct over 0.8 mm. 1 mm is 0.1 centimeters. Okay, yeah, this is 0.08 into 63 centimeters along this distance. So this distance we quickly know. I remember this to be 7.1 centimeters. So the additional distance you should travel is 7.1 minus 5, right? So that is the additional. So if we draw a circle here, this 5 centimeter is common to both. This extra distance traveled by the wave from this transducer is 7.1 minus 5. The time taken, divide this by the speed. Are we given things in speed? Okay, sound wave, assume 1500 and 0 centimeter per second. We should get the time. 0. Notice this is in centimeter per second. So we get the answer in second. And finally, we want things in microsecond. Okay, what do we get here?
14 microseconds.
So roughly 14, 9. Can one of you type the decimals following that? And whether you use
Exactly 14 microseconds.
oh, exactly 14 microseconds. Okay, this is fine. Okay, we get to MRI. See, suppose thing gets over by MRI. What is the time on? Yeah, MRI. Let's quickly pick up this. Okay, this quickly. What is the answer for this? Okay, let's say this is an short TFO. PD weighted, long TR and no differences between TR, no differences between TFO. We should get a PD. Yeah, this question by no, it's a simple question. It looks actually very complicated. I thought this was one of the hardest questions. Okay. So volume of the slice is this. So volume slice is being halved. Okay, so V2 over Vs, one of the factors become half, volume becomes half. And this 1 Tesla and 3 Tesla. Be careful of that, be whether it's 1.5 Tesla or 1 Tesla, 3 Tesla, be very careful of that. So if you change the Tesla emission B0 it will affect gamma naught and m naught. Okay, so that we have a factor of b naught square. So we have this times. So of course the signal is going to increase because we go to a higher machine. So it's a by 1 square. So this is, see, this is 4.5, 9 by 2, which is 4.5. Okay, apply an RF pulse to a sample of protons, sample an equilibrium, strength of the RF excitation. You need to tip the magnetization to in 3 milliseconds into the XY plane. So this means we are talking about, pi by 4 is the tip angle. What does the tip angle depend on? 2 pi gamma hash. Notice we are talking about radians, pi by 4 radian. So use 2 pi gamma dash, where gamma dash is 42.58 megahertz per Tesla. Okay, and this times the magnetic field in Gauss, right? So B1 times tau p. Tau p is going to be 3 milliseconds. Is 3 milliseconds. So we want the field strength in Gauss. So remember 1 Tesla is 10 power 4 Gauss. To use that, okay, our B1 should turn out to be, this pretty small number, 0.196 Gauss. Notice this is 0.196 into 10 power minus 4 Tesla. B1 is much orders smaller than the main, 1 Tesla, 2 Tesla machine, 3 Tesla machine. Fine.
In this, why you take pi by 4?
Why I took pi by 4? So it says we tip it to the XY plane, the transverse plane. Magnetization vector is aligned along B0. Okay. We tip it to the XY plane. The XY plane is perpendicular to this. So we tip it by an angle of 90 degrees, that is in radians, that is pi by 4. The tip angle is pi by 4. Oh, pi by 2, right? Yeah. 90 is 90 is pi by 2 pi is pi is 180, pi by 2. Thanks. Okay. Yeah. That pi by 4 2 is a confusion. Thanks. So this is pi by 2. Okay, so I am actually running short of water. I'm feeling thirsty, but that is fine. Let's just continue on with this. So the rest of you will have to quickly fill up this. Okay, isochromats. This is supposed to be, question looks somewhat very, very tricky, but at the end of the day, if you're careful about units, you know what is going on. It's a very, very simple question. There is a fractional difference of 20 ppm. Okay. So delta nu is going to be gamma hash. 391. So can someone help me with all the steps here? What should be this? So what is the phase, the frequency difference between those two, and then how does that change to phase difference?
Yes, sir. So here we calculate gamma B naught, and here we'll go from mu2 minus mu1. So
okay.
First we can just simply calculate del mu is equal to gamma hash into B naught.
One second. So when we say there is a fractional field difference, is this B naught dash is B naught into 1 plus 20 10 power minus 6. This is correct, right?
Yeah, yes, sir.
Minus.
Yeah, plus or minus. Okay, so that the phase difference really doesn't matter. B minus. So the change in frequencies will be the difference between these two. So that will be 20 into 10 power 6 times B naught. So this is how the change in frequency is. And we want the frequency in which units? If you want to retain the frequency, if you use gamma dash as 42.58 megahertz per Tesla, okay, this is in Tesla. So we should get this answer. If you plug in this B naught and this value, you should get this in hertz. I mean hertz or megahertz. So roughly, what do we get here?
So we get
PPM. Oh, -6. Yeah. 1277.4. Thanks. So change in precessional frequencies is this much. So yeah, these many times in these many revolutions in 1 second. Okay. So how do we do this?
we calculate for half a revolution how much.
Yeah. Okay. So these many revolutions take 1 second. So half a revolution takes 180 degree is half a revolution. This by 1277.4. Right?
Yes, sir.
Yeah. Thanks. This is so. Yeah. In 1 second we have these many cycles. Half a cycle will take half by this, and that answer is
391 microseconds.
thanks. 391 microseconds. Great. Thank you. Minimum time and MR scanner legally established. Yeah, we need to remember one detail here. What does the FDA approve? What change? 40 Tesla per second. Okay. So, okay, we need a gradient of 50 millitesla per minute. Human body, we need the distance, right? Like, okay, per meter, it's just roughly we are talking about. Yeah, we need to approximate things here. We need one more data. Roughly, what is the breadth and width of a human body? It's 0.5 meters. Okay, so if we use that, what should we get here? So the maximum gradient is going to be 40 millitesla per meter into 0.5 or 0.25. So something on this side and something on this side. So it should be 0.25. Okay, d by 2, diameter by 2. The maximum change here is how many milliteslas?
10.
Okay, 10 milliteslas. Okay, we are allowed 40 teslas per second. So in order to go to 10 millitesla, how many milliseconds? This is time is distance by speed. So 10 into 10 power minus 3 by 40. And this is
0.25 milliseconds.
yes, 0.25 milliseconds. Okay. Sample is put in a magnetic field with B naught as this. B naught is this, Z gradient strength with GZ is this, maximum value of normal frequency within the slab. Yeah, we can say the range, this, that, and all that. So our mu is going to be gamma hash times B naught plus GZ times C. Okay. So it's 3 Gauss per centimeter. So GZ is 3 into 10 power minus 4 Tesla per centimeters. And slab thickness is not given, that should be given technically. Okay. I suppose the slab thickness is not given, right?
Yes, sir.
Yes,
Yeah.
sir.
That we can't solve this without slab thickness. Slab thickness needs to be given. Anyone remember a typical value from the book? Okay, slab thickness is 0.5 meters. Pretty high. Okay, 0.5 meters. Okay, so so this is 25. 50 centimeters. So the maximum will go like 25 centimeters to this side, 25 centimeters to this side. So our new max is going to be 42.58. Answers on megahertz. So I'm going to leave this in megahertz per Tesla. Megahertz per Tesla. And 1.5 plus GZ, that is 3 into 10 power minus 4 Tesla per centimeter into 25. So we get answer. So the frequency, so yeah, 64.118 or 18. So we have like center is here. This side is maximum occurs at 25 centimeters. That is 50 watt. Suppose we design a size thickness of 2.5 mm, Z gradient is this, R of pulse bandwidth to escalate the status. Okay, how do we do this? The same thing they are asking in the other way around, right? Quickly, oh no, this is
We're using range of formula.
using
Range of frequency formula delta V is equal to gamma S Vz delta Z.
okay. Oh, okay. This is just the change in frequency. Is that what they are asking? Yeah, the R of pulse bandwidth is at the end of the day, it's bandwidth is change in frequency. So there should be gamma Z, GZ, delta Z. So delta Z is now let's get everything. This is 1 Gauss per centimeter. So this is 1 into 10 power minus 4 Tesla per centimeters. This is 2.5 mm. So this is 0.25. 2.5 plus 0.25 centimeters. Okay. And so we know delta Z, we know GC, and then we also gamma hash by now we should know that 42.5 megahertz per Tesla. So we want the answer in kilohertz. So if we convert this into kilohertz, put a 10 power 3. So this is into 10 power 3 kilohertz per Tesla. So just gamma hash is this, delta Z is this, GZ is this. We plug in that, yeah, 1.06 kilohertz. Okay, I think we'll go till like 45 or something like that. Okay, roughly 8. Else I need a 2-minute break to grab my water bottle. Else it's hot for me to sleep. Suppose that we deserve a thickness of this or a frequency range should be excited. So yeah, delta nu is given. Duration of the main loop and first 2 side loops of the R of pulse required to achieve this. Yeah, we spoke about this. If you want frequencies in the range delta nu, the corresponding sync wave we are looking at is delta nu times t, right? And the first loop will occur at the first 0 will occur at this equals 1. Delta nu t equals 1. We have the first loop. So from this, we can find T for first one loop. Okay, and the answer what we want is time duration for main lobe that has two, the 2T that we are finding here, and then on the two side lobes. Each lobe has a T, so plus T plus T. So T is 1 by delta nu. Answer is 4 times 1 by delta, 4 by delta nu. What is that? For others, let me also quickly draw what this first loop, second loop is. Same function looks like this and this. So this is at 0, 1, 2. So this is where we equate. The first 0 occurs at 1, so delta mu T is 1. So this is T. The size of 4 lobes is then 4. Yeah, suppose that is correct. 3.77. Something slightly 1 millisecond is this, this lobe. So 4 times that is 3.77 milliseconds. Okay, now the K-space sampling, this, that, and all that. We could quickly do sample of photons. We want to scan a line segment in the K-space. U max is given. U is 0. So roughly delta U is gamma hash Gx into the readout, duration of readout, and this is Ts. So we just need Ts, right? So 0.5 centimeter inverse. Okay, that is delta U. This is 42.58 into 10 power 6 megahertz, hertz per Tesla. That times, so that times cos, so that is 1 into 10 power minus 2 cos per centimeter, or sorry, Tesla per centimeter, times Ts. So notice if we take everything to this side, we'll get Ts in seconds, convert that into milliseconds, we should have 0.117. Yeah, 2 of you have the number, so we'll take that from it. Okay. Rectilinear in a rectilinear fashion, number of lines covered in Fourier spaces. Yeah, we have to make some fast. How do we do this very, very fast? One of you? This is one of the harder questions from MRI, but I think we just did this recently. Any one of you can quickly say how to do this?
First, we should calculate del nu. Then we'll calculate the U max minus U minimum. And from that, we'll calculate number of squares. That is U max minus U minimum by 0.127.
Fine. And del nu, I suppose you could calculate from okay, T phase gradient is given. Then Gy is not given, right? How do you find del nu?
So mu is equal to del Gy is 0.1 in class, you gave value.
Gy, yeah, Gy is supposed to be given here. So yeah, this is del Gy. Else the problem doesn't make sense. Okay, this is incremental changes in del gradient in y direction. Given that this is delta Gy into T. Yeah, we can find del nu. Then to find nu max, I think there is a square mentioned, right? It's square. So nu max minus Newman is Umax minus Umin. So Umax minus Umin we can quickly find out. So Umax minus Umin. Umin I suppose is 0, start from 0 to 0. So Umax is gamma hash Gx into readout gradient time. Where is readout gradient time? Ts, 3 milliseconds. Okay, Ts. So, and what is so Umax quickly? What is the answer for this?
12.7.
12.7 something centimeters inverse. Okay, so this del nu we get that to be 1.27.
0.127.
0.127 centimeter inverse. And so that means, so this is also going to be, if we start at 0, 0, 0, you minus this V max or del V max, the total change in the frequencies in the y direction. So our n number of lines is V max. Technically, it's minus V min. So we are presuming that, let's say this V max minus V min. So that by
Del nu.
yeah, del this change in frequencies, let me not write it as mu max. There is a total change in frequencies. Length of the square region is a total change in frequencies. And so this is 100 or something like that.
101.
Okay, 1. We have discussed lots of questions. Some of them are actually very advanced. For example, this question is slightly advanced. Even we are prepared for that. So if you have been following along, you're in good shape. You should score very well in medical imaging, and we'll do the same thing for biomechanics and subsequently for bioinstrumentation. Okay, so that's the plan. Okay. And in part 2 of this video, we'll cover the rest of the questions. This is part 2 of our mock test discussion. So this mock test, subject-wise mock test, has both medical imaging and biomechanics. We already covered most of the questions from medical imaging, and so we'll cover the leftover questions and then we'll dive into biomechanics. Where okay, suppose we did till this question, okay, 43rd question, 44th question. So we have about actually we have like close to 10 medical imaging questions. Anyways, let's quickly go through them. Let's also do this thing pretty fast. So general feedback, where you're able to solve these problems. Like, okay, we have about, like, I suppose 40 questions left. How many were you not able to solve or find solutions for? Were you able to solve most of the questions? Quickly.
Yes, sir.
Thanks, Nandini. How about others? Samson. Okay, 3 to 4 in imaging, were you not able to solve it, or were you?
Yes, a few problems relating to MRI, like here and there. Rest all I was able to solve, sir.
Okay, few problems related to MRI. Okay, so let's do this. Let's quickly, solve where we left off. Okay, quickly, the field of view of an MR image is related to the sampling steps in Fourier space span. Suppose a reconstructed MR image has the same resolution and size in both F and E. Okay, so given this AS, GX, FS, okay, we have to find the size of the field of view. Okay, and the same resolution in X and Y, so the field of view is also, let's say, the same in X and Y directions. Okay, how do we do this? So quickly, what is this number? What is this number? TS is the signal acquisition time, and what is FS?
Frequency.
Of what?
Radio frequency.
Frequency of no. This Fs sounds like the speed at which you acquire the signals, right? Okay. So what we need here is, so we know field of view in the x direction is 1 over the spatial frequency. So your field of view, sorry about that. Okay, so field of view, we have things in x direction and field of view in y direction. Field of view in x direction is, this sampling, change in sampling frequency, spatial frequency in the x direction, right? Similarly, field of view in y direction will be 1 over del b, the changes in delta changes in the y direction. Okay, so I think from gx, then we have gamma hash. Let's say that is 42.5 megahertz per Tesla. Okay, can we find delta u from the given information?
Yes, sir.
What would that be? Yeah, so this is the 1 over gamma hash into gx into the sampling period, right? So how fast we sample things. Okay, and this should be 1 over f of s. So this is period. So from frequency to period, there should be 1 over that. So we have 1 over gamma hash into gx times fs. Okay, and so now we know all the things. We can quickly find the field of view, which is also, it is the same in both the directions. So this is 85.33 into 10 power 3 into 10 power 3 by, we have a Tesla to Gauss. Let's keep this in Tesla. Let's convert this into Gauss. So we have a 42.58 into 10 power 6 megahertz per Tesla into, this will be 10 power minus 4 Tesla per cm. Okay, yeah, per cm. So the answer we'll get will be in centimeters. And what do we get for this number? We have 2.03, 20.04. We have a mix of answers. Which number is correct? Let me check figure that. 3 into 10 power 3 divided at 42.58 divided at 10 power 6. This number at 20.03. 20.03 centimeters. Okay, so this is, this is like how frequent do we get the acquisition signal? So 1 hour, that is the time period here. Okay, distance between two samples. Okay, and TS is the total acquisition time. We do this for TS seconds. Okay, so with this data, we can just find out what this field of view is. And here, the resolution
I have a doubt.
Yes.
So generally, when we calculate del U, we are using TS in previous problems, and here why are we using FS instead of TS?
1 second. Did we use TS?
Yes, sir.
See, this is the total. This is V, right? U max. This is the u direction from this total distance in u is gamma hash gx ts. If you notice, what is that distance between two spatial frequency points? That is delta u. That should be gamma gx into the distance between two samples in ts, right? That is the t that we have there. Fine. So, okay, let's say this is where we acquire the signal for a length of, this length is ts. The signal acquisition happens every delta t, which we call as t here, this distance between two samples. Okay, so that 1 over t will be our sampling frequency in this, for this signal. So distance between a point here in the k space and a point here in the k space will be just depends on how far away these 2 points are, right? It moves in the k space based on how, you know, how long this time is. If it is just small part of that t, just goes by delta u is just gamma gxt. Does that do you see the distinction between ts and this t?
Yes.
Okay. Yeah, and notice, yeah, here we are looking at Umax. That is, what is the entire distance between left and right? Here we are just looking at what is this del u. If you know, at the end of the day, if we have like n pixels, n times del u should be Umax. Okay, this times n should be Umax. So there's just a point distance between consecutive points, and that is what we are looking at here. Field of view is not 1 over u max, it is 1 over del u. So given that we use distance between two consecutive points, okay. In fact, can you quickly calculate what is t? That is 1 over f. .7 I think microseconds. 55.33 divided by 10 over. Yeah, 11.77 microseconds. Okay. Suppose this times 256 is 3. T times 256, notice, which is the pixel size is not given here. Okay. That is number of pixels in the x direction. That is 256. So if you multiply this distance between 2 points in the spatial domain, that times 256 should give you actually the signal acquisition time. This should be equal to this. In fact, 11.7 microseconds times 256, what I have is 3.0 milliseconds. Yeah. So this t is, in fact, it's at least, yeah, for this question, if we know 256, this is redundant, but because, yeah, 256 is not given in this question, ts is given separately, but here we don't need that. Fine, things are clear, right? At least what is what, where to use for.
Yes, sir.
Yes, sir.
Okay, then let's go to this one. The resolution of an MR image is related to the case-based coverage by Fourier transform. Want to acquire 256 by 256 image with resolution of 1 mm by 1 mm. Okay, now we know the pixel resolution, number of pixels, and then readout gradient is this. And this is repetition time. And what we want is the imaging time is. Okay, so, okay, in fact, this is a much simpler problem compared to what is given in this book. It says in one repetition, we can get repetition. We essentially get 256 points in the case space. Okay, This is essentially one row we get. One row. Now, how many rows should we get? We need 256 rows. That would correspond to 256 times TR. So just multiply TR and 256. What do we have? 2 10 into 256. 12.8. Yeah. It's a simpler question. The reason is we haven't seen something known as full width at half maximum. We look at this during our image formation class. So once we look at it, we'll also look at that advanced problem that is given. But this problem is very, very straightforward. Okay, radioactive of radionuclide. So that this completes MRI. And notice, see, we did not leave out any examples from the book. So even almost all non-trivial examples in the book we have covered for ultrasound for pretty much all the chapters. So this list is quite comprehensive in that sense. And now we move on to radioactivity. Radioactivity of radionuclide, decay constant is this, and it's 6 millicurie. And the radioactivity of the radionuclide at 4:30 p.m. on the same day will be, okay, we start with this radioactivity A0. Okay, we deal with radioactivity, that is decays per second, in Curie. So this is A0. This is again exponentially decays, e power minus lambda t. And so what will be this value after so and so from 10:30 to 4:30? How much time does it, how many hours is that? Quickly. 10:30 a.m. same day. So
6 hours.
6.
Thanks. 6 hours. So we should quickly get this. Start with millicurie. So your answer should be in millicurie. Okay, 6 into e power. Lambda is in seconds or second inverse. And so let's also convert the 6 hours into seconds. 6 into 1 hour has 60 minutes, and that has 60 seconds. Okay, so this many number of seconds in 6 hours. And whatever this number is, this is in millicurie, and we should get our answer. So what do we get if we calculate this chunk? 2 point. Okay, I suppose all of you are getting this. Thanks. So 2.99 millicurie. And be prepared with any unit things just in case they ask this in becquerels, 10 power something. Be ready to answer that. So what is 1 curie? Suppose it's, can you get a quick answer in the chat?
3.7
Into 10
into
power
10 raised to 10.
10 becquerels. And 1 becquerel is essentially 1 decay per second. 1 decay, whatever particle it is, 1 decay per second. Then here we have this problem. A radioactive isotope in nuclei are needed to produce radioactive level of 2 millicurie. Assuming decay constant, okay, the same decay constant. Now atomic weight is given, Avogadro number is given. Mass of the radionuclide in picograms is, okay. Now this, we have to do some mole conversions, right? How do we do that? Radioactivity. First thing, notice boils down to this relation. Here, radioactivity is number of decays per second. That is, our A will be equal to n times lambda. Okay. The idea is we start out with, okay, our A is n times lambda. We know how this relation shows up, right? We just take the number of nuclei divided by d by dt with a negative sign because it always decays. With that, you get the activity. This is activity. Okay, that should be at least A naught should be n times lambda. Okay, and that is what is given in this question. So our number of nuclei should be equal to activity divided by lambda. And this is just number of nuclei. Now we have to convert that into mass. Okay, so let's quickly, this is 2 millicurie, this is 2 into 10 power minus 3 into 3.7 into 10 power 10 particles or decays per second. Okay, decays per second, and then we'll have, if you divide this by 3.22 into 10 power minus 5, okay, this is per second, so we have 1 over s, they will get cancelled. So these many decays or these many number of particles is what we have. And the number of moles here will be 1 over the Avogadro number, Na, that is 6.023 into 10 power 23 moles. So these many number of moles we'll have here. If 1 mole weighs 98 grams, this many number of weighs how many grams? So into 98 gram per mole. So the mole should get cancelled. Now, what is this number? And we want that in picograms. So I suppose 10 power minus 12 grams. Quickly, so what is this number become? 374. 374. Okay. Rounded off to nearest integer, that would be 373 or 374. Okay, so 373 picograms. And this distinction is important because radioactivity is n times lambda, and that shows up from this relation. Radioactivity is decays per second. Okay, shows from this. And this problem, okay, CT problem, some of the problems we have done in class. So this involves 2 types, right? So this is for a 1G scanner, you know, things are much simpler. So it goes with a thing of 1 meter per second. So it has to do 2 things. One is linear traversal. Second is rotate after traversing, right? Rotate. And one traversal would take, it has to traverse 0.5 meters at a velocity of 1. So this should take 0.5 by 1. So suppose that is 0.5 seconds. Okay. And how many times should it traverse? That comes from the, we have to do 360-degree projections. So it has to traverse 360 times. Okay. 360. And number of rotations. So from one traversal to another rotation, it kind of takes 1 angular increment. So this again takes 0.5 seconds. Number of rotations here is 360. So the total time will be 360 into 0.5 plus 360 into 0.5. Suppose this is 360 seconds, right? Simple question. This we have done in class. For a technetium radioactivity 1 millicurie, the intensity at a distance of 20 centimeter in kilo electron volt. So I suppose we need the energy for technetium radioactive decay, right? Anyone know that value? Because this is in decays per second, we should have energy of 1 10.
So 140.
Okay, this corresponds to 140 kilo electron volts. So what is going on here is the source, we have radioactivity is 1 into 10 power minus 3 decays per, so into 3.7 into 10 power 10 decays per second. Each decay will give this much amount of energy. So this many number of decays will give this into 140 into 10 power 3 electron volts. This much amount of energy, okay, per second. And we want the intensity at a distance of 20 centimeter. So divide by the area of the sphere at 20 centimeter. So 4 into pi into r square, and that would be 20 centimeter is 0.2 meter square. Okay. So this answer should be in electron volt per second. The second electron volt we got from this, per second we got from radioactivity, and then meter square we got from this meter square. So we have things in kilometers. So let's forget this 10 power 3. So if we calculate this, we should get the answer kilojoules. What is that? We are getting slightly different answers into 10 power minus 3 into 3.7 into 10 power 10 into 140 divided 4 divided 3.14 divided 0.2 square. I get this is equal to 1.03 into 10 power 10 kilo electron volt per second meter square. Yeah, I pushed the 10 power 3 into this kilo directly over here. That's the answer. Yeah. And typically what they will give and get us, the blank will be like this. This times 10 power 10 kilo electron volt per second per meter square. So that you could enter 1.03. And the pulse height analyzer is used to reject photons, so and so. Okay. Now, okay, pulse height window is 20%. So we know we will accept things 10% in this side, 10% to this side. 10% in this side is 154 kilo electron volt. 10% in this side will be 130, 126 kilo electron volt. The previous question, they are likely to provide this one in gate exam. This is something that we don't expect, typically to remember. But these numbers, this Curie to Becquerel 3.7 into 10 power 10, that they don't have to do. And E value varies based on what the nucleotide you are using. So it wouldn't be fair if they don't do this. Okay, so 10% on either side. So in this side, this boundary will be 126 kilo electron volts. This boundary will be 154 kilo electron volts, and we are looking at Compton scattering. So specifically, that should have a reduced energy, right? And we are concerned about anything below this energy, we will know will reject it. Okay, so how can we quickly get the relation here? Compton scattering relation, anyone remember that? Suppose cos theta is 1 plus mc naught square into, is it 1 over E naught or E scatter? E naught is
E naught
higher.
minus E scatter.
Yeah, E naught is higher. So this is a negative term, and this becomes slightly less than 1. Okay. E naught by ES. Remember, this can save you tons of time if you deal with this way. We know E naught is 120. Sorry, E scatter is 126 kilo electron volts. E naught, the actual value is 140 kilo electron volt. And then m naught, mc naught square, they will typically give you mass and velocity. Okay, even if they don't give that, the energy corresponding to that we know is mc naught square is 511 kilo electron volts. This is one number that is worth remembering. They will typically give you conscience for that, but these calculations are in kilo electron volts, so it helps to remember this one number. Okay, if you have this, what is the angle for theta that you get? Theta should be cos inverse of that. Quickly, what is the value here? If I suppose Samsung's answer is 53.5. Any other answers? Okay, all of you are getting that. 53.5 degrees. Consider an anchor camera with a square multiplier. Okay, this again is something we have already seen. A simple CG problem. So far it hasn't shown up in GATE, but it can either show up in biomechanics or here. Okay, all we have to do is we are given, okay, we have to find X locations, okay, for 1 to all this 9 points. The X locations are roughly over here. And the pulse heights recorded in H is given over here. This corresponds to 1, 2, 3, 5, 6, 7, 8, 9. 9 points and 9 X values. The X values quickly will be Xi will be in the order. For the first value, it will be, we want things in mm, so I'm going to keep X in mm. This should be -2, 0, 2. So this is at -2, 0, 2. Then we have -2, 0, 2, 0, 2, and then -2, 0, and the ninth one is at 2. Answer we are looking for is X bar should be sigma Xi, this pulse height. Call it Fi by sigma Fi. Okay, and what is given over here is the pulse height. Each of the things. Quickly, if we calculate this, what do we get? I think this is the sigma Fi is known as, always remember one more terminology, that is the Z pulse. Sum of all this should be Z pulse. Okay, thank you. 125 and Xi Fi divided by this X bar should be and remember okay, for this problem it's a simple formula, you could always do that, but the number you are expecting somewhere over here. Okay, so 5, 10, 15, 10, 40, 30, 0, 5, 10. So yeah, somewhere within this window is where we are expecting the answer. Okay, 0.64 points. And this question, yeah, simple question. Multiple gated acquisition mode can be used to study beating hearts. In this mode, each cycle of the acquisition is triggered by R wave of the ECG. Okay, suppose the heart rate is 50 beats per minute. We want each frame to last for 75 milliseconds. Okay, one frame is 75 milliseconds. How many frames can be there in one bit? Okay, so 50 beats, 50 beats per minute. Okay, so 50 beats per minute. That corresponds to 50 by 60. Each minute has 60 seconds, so 50 by 60 beats per second. So what is per second? We have like what percent of the beam? 50 by 60. So per second we have like 0.83 beats. Okay, beats per second. So what is length of one beat? One beat corresponds to 1 over that, 1 divided 0.83. That should be 1200 milliseconds. Okay, this is just 1 over 0.83. So our total length from R wave to R wave is 1200, and one frame will be 75 milliseconds. How many such frames can be there in this length? And all these numbers are carefully chosen such that we have an integer here. Yeah, 1200 by 75. And that I suppose is 60. Be very, very convenient with all these calculations. This is some question that again hasn't showed up yet. ECG, beats per minute to length of RR waves. Okay. In fact, notice one other standard thing they could ask is what is the length of RR waves? Okay, that is distance between two R waves. Just calculate that here. There is also something they could ask. Suppose a single head system requires n counts in a 30-minute scan. Okay, and let us imagine performing the same study with a two-head system, and the two collimators have higher resolution with 70% of the sensitivity. Okay, so if we use one thing, we get like n counts in 30 minutes. Now we use two collimators. Okay, so again in 30 minutes, okay, we should get 2 times the sensitivity is reduced only 75. So 2.75 into n. So one of them will get 0.75 into n, two of them will get 2 times this times n. Okay. So in 30 minutes we get this much. So in what time? 30 minutes we get this much count. So in 3 minutes, so this is what we have to find. That would correspond to n count. So quickly, simple ratio problem. So t over 30 should be n over this number. Okay. So t over 30. This ratio should be same as this ratio. That is 1 over 2 into 0.75. So 30 divided by 1.5. So answer is in 20 minutes we can do it. Okay, great. This question, okay, quickly gate 2020 question, but let's quickly solve that. Remember all those things: numerical aperture, field of view. Okay, all that. Numerical aperture would be root of n1 square minus n2 square, right? So sine theta a is this the critical angle that will be numerical aperture. So we can find theta a from these two information, and then field of view is twice this theta. Okay. So this implies theta a is sine inverse n1 square minus n2 square. What is theta a here? Theta a is 22.58. So we have a cable, we have this thing. So anything within this will get totally interlinear affected. Anything outside of that will not get affected. So things within this field of view will be recorded. Okay. And notice, just in case they want the field of view in length, you should be looking at this one. Right now, field of view is in degrees, so we gave this angle. Okay, sometimes they might want field of view in length. Then you should be finding this distance over. Okay, so for finally, what do you get? Yeah, this is 2 times theta a should be 45.17 degrees. Okay. Chest radiograph is this. And this is another question that we haven't discussed so far. We look at this in image formation class, but very, very quickly, okay. So we have one pixel date, one image source here, another image source here. Okay, this is one cycle, that is things that we can distinguish: a peak, trough, and a peak. Okay, and one cycle, there better be 2 pixels here. 1 pixel to capture this dark spot, 1 pixel, half a pixel in this side to capture this bright spot, and on an average half a pixel in this side to capture this bright spot. So we have one cycle will corresponds to 2 pixels. So 6 cycles per mm essentially means at this resolution, the number of pixels we need will be 12 pixels per mm. So below this, we hit upon something known as the Nyquist frequency rate. We cannot capture the image properly. Okay, so per mm, then things are all fine. Now, this is the size of the radiograph. Based on this, can we calculate the image size in MB? It's a very simple problem. Take the x direction, that is 360 mm. That should have 360 into 12 pixels. Okay, then we'll also have pixels in the y direction. This multiplied by number of pixels in the this times this row times column. So this times 480 mm in the y direction. 1 mm will have 12, so 480 will have 480 into 12. Okay, so these many number of pixels. Okay, and per pixel we have like 8 bits. So these many number of bits. Now we want things in megabytes. How do we convert this to number of bits to bytes? You divide this by 8 ones, you get answer in byte, and divide this by 1024 ones, you get answer in KB, and divide this by 1024 again, you get answer in megabytes. So the key detail here is this. Okay, this we haven't seen so far, but I'll explain. Okay, cycles, line pairs, pixels, and all that. What are all things they can ask? I'll explain that. But given this, so these many megabytes of data would be needed. What would that number be? Okay, thanks. That should be 23.73. Close to 24 megabytes or something. Okay, now this is the end of medical imaging. We have a few questions from image formation, signal to noise ratio, and all that. And we look at that SNR for pretty much will cover what would be the signal proportional to ultrasound, MRI, CT, radiography, all of them together. Okay, along with some other details like how do we pixelize things, what is the resolution, how is it quantified and all that class. So this is still left. We look at it in a separate class. Okay, now let's move on to BM paper. Okay, at this, before we start the BM paper, can all of you do one simple exercise? Take the GATE BM 2021 paper. Tell me the marks corresponding to non-core subjects, that is signals and systems, analog and digital electronics, control systems, measurements, and electrical circuits. So all of them put together, how many marks out of 100? Can you all individually ping me this number in phone? I don't have many of your, lost many of your contacts. So it would help if you ping me this number with your name also if possible, if already we are not talking. Can you all do that?
Yes, sir.
Yeah, the point of this is to actually, yeah, thanks. 30, it's slightly higher than 30. Okay, 30 is a good guess. The point of this is to actually see, we started with core subjects. Why start with core subjects? this is one of the hardest papers because there were actually, students who gave the exam last year. Where are core questions? They were searching for questions that they were more familiar with. Okay, so this was like core biomed unfavorable paper. Even in that paper, the maximum was 35. Okay, so worst paper, corresponds to 35 marks. We have covered pretty much the other 65, close to 65 by now. Okay, so anyways, do this exercise and get me a proper number. Okay, let's get started with biomechanics. And again, I have a very decent list of questions from biomechanics. Pretty comprehensive. Well, comparing parallel fiber pinnate muscles. Okay, this quickly. Pinnate right now, we know parallel can like really shorten. Pinnate can apply more force at an oblique angle. AB, that's correct, right? AD. Okay, thanks. Then 60% standing on a trochanter kneeling. Okay, for the practice, let's quickly do this. Okay, there is no equilibrium and all that. You just have to find the thing. Let's say this is the ankle. Okay, the trochanter knee and all, knee trochanter is over here. Let's forget that. From the ankle, we have a 60 kg person. Ground reaction force is found to act at 40 mm anterior to the ankle joint. This is the anterior direction. So this is where the force are. 40 mm, the entire reaction force is acting, and this corresponds to 60 into, remember, 9.8, or at least 10 to get the force. This is just mass, and then we have the weight of the force, which is elsewhere, right? 60 mm. So somewhere acts over here at 60 distance, 0.8 into 9.8. What is the net moment? That should be 60 into 9.8 into 0.04 minus 0.8 into 9.8 into 0.06. Subtracted because they are acting in, one is in counterclockwise, other one is in clockwise. So this is the net moment. This should be close to 23. Okay. In fact, notice compared to 60 kgs, this is hardly providing any moment. Even if you just calculate this value, you could answer this. Okay, this problems we have seen in class right very well. Let's quickly do this. F1 is this. So F1 is 15 acting at a degree 30 degrees. So F1 will be 15 cos 30 degree in the I direction, the X direction, that is 15 sine 60 degree in the K direction. Sorry, IJK. This again sine 30 degree in the J direction. Okay. Just taking trigonometric components along this direction, this direction. And quickly, F2 will be, notice this is in the negative X. So if we use beta as 45, we have beta. So minus 10 times cos of beta, that is 45, the I direction, plus 10 times sine of 45, this along the Y direction, the J direction. From here, we can calculate the resultant, F1 plus F2. Okay, so this also we can calculate, and then okay, let's quickly. Can you tell me what this resultant is? 15 minus 10. Oh, no, there's cos 30 cos 45. Okay, can you quickly tell me what is the I component here and the J component?
5.9.
5.92. Okay, 14.57. And so this is, adding these two, we get this component wise. And given this, we can also find this angle theta. Notice when theta is defined with respect to y axis, So x component by y component will be tan theta. Okay. So this implies theta will be tan inverse of x component, that is 5.92 by 14.57. Okay, we also know the angle at which F4 acts, then other things should be fine. So what do we get for this angle? Suppose, so this is 22 degrees, 22.1 degrees. Okay. A very, very basic problem. How do we, what do you mean, how do we treat force as a vector? Okay. Then let's also quickly do, we did a couple of cases in the class. Okay, case 4, this is acting along this side, this is acting along this side. Perpendicular distance from 0 is 0. So case 4, we can directly say, case 4, the moment is 0. Okay. Case 1, the moment should be this moment plus that moment. So both of them are in the same direction. So weight 1, so that is 15 newtons, and it's acting at a distance of 0.2 meters, plus boot is 100 newtons, it's acting at a distance of, why is there W by, okay, it's not, it's case 2, that's acting at a distance of 0.5 meters. So case 1 moment also we can easily say. Case 3, I think we have done. Okay, this is, 50 plus 10, that is 60 Newton meters. Okay, careful about the units. Let's do case 3, because that's something that we haven't done. So case 3 is this. For clarity, we have the vertical line. Okay, what was here at 20 centimeter? Okay, now things are at an angle 60 degrees. So this angle is 60 degrees. What was here kind of moved to this point. What was here kind of moved to this point. So obviously corresponding to that, their moment arms, that is this distance decreased. So moment for case 3 should be force into perpendicular distance. So we have 50 into perpendicular distance, in this case will be 0.2 cos 60 degree plus 100 into this distance will be 0.5, again cos 60 degrees. So this moment. Is it 30?
Yes, sir.
Okay, 30 Newton meters. So this is in Newtons, this is in meters. So we get it in Newton meters. Okay. Then let's also quickly do this problem, one full problem. Okay, so we already discussed what is free body diagram and all that. Now I'm going to draw, what we have to do is to find the reactions at points A and B. So we have the person, let's just pretend this is a person for the time being. So there is one force acting, his weight acting downwards. He is in equilibrium because, of course, there is one more force that is acting upwards. Okay. Else he cannot be in equilibrium. Right? So the reaction force in order for this person should be equal to in order for this person to be in equilibrium, the reaction force should be equal to the weight. Okay. Now let's draw the Planck. Okay. And notice this comes from force equilibrium, pretty much Newton's second law. The reaction, so if this is action, then its reaction should be somewhere over here. Again, the weight of the person should be there. Then we have the weight of the Planck, I suppose. Weight of the beam is 900 newtons. Okay, so this is 900. Weight of the person is 60 into 9.8 newtons. And we'll have, this is a hinge, this is a pin. So what we have done so far, we are trying to draw the free body diagram. We have isolated the person. We have also shown the effect of gravity. We have to show the effect of the pin, Ry, this is Rx, and then this is just a roller. So there is one unknown. Let's call that, Ry2. Quickly, sigma fx, only one force in the x direction, that better be 0. Okay, so I'm writing this. So this implies Rx, no other force in x direction. So this reaction force is 0. Then we know we can find the moment equilibrium either about point A or point B will involve only one unknown. So either right about this point or right about that point, you could find the one of the forces. Let me write it about point A. Okay, this is 0. What we have here is, let's also give a direction. This is counterclockwise is positive. So Ry2 times its moment arm is that given. The entire distance is L is 5 meters. Okay, that minus moments due to this 900 into 5 by 2. The moment arm of the weight is at the center. When the person is standing at a distance of 3 meters, so minus 60 into 9.8 into 3. Yeah, one is at 2.5, one is at 3. This should be 0. From this, can we quickly calculate what is Ry3? So Ry3, just that's the only unknown. It's equals to 0. Sometimes the dots they keep disappear in this file, so just be careful. 900 into 2.5. 60 into 9.8 into 3. 4014 divided by 5. Right? 4014 divided by 5. Yeah, this is 802.8. All these things are in Newton meters. So yeah, this should be in newtons. Once we know Ry, we can finding this Ry or Ry1. That's pretty easy. You could. My suggestion is do this so that you don't get confused. Sigma Fy is 0. So we have. Let's also assume this to be the positive y. So we have Ry plus Ry2, all the forces in the y direction. That is 802.8 minus 900 minus 60 times 9.8. All of them should be 0 so that it's equilibrium in this direction. This implies R1 is 900 plus 60 into 9.8 minus 802.8. Okay, 685.2 newtons. Okay, simple question. So notice, in fact, here we have solved the entire problem starting with free body diagram. We have pretty much 3 unknowns. We know 3 equations of equilibrium. Fx is 0, Fy is 0, moment about any point is 0. We wrote them in a convenient order. Okay, great. Yeah, this is another namesake problem just to make sure the center of gravity equation is possible. Just like that pulse height, locating the pulse height, we need to locate the CG, and I suppose CG of the entire leg. So we have 3 parts, part 1, part 2, part 3. Each part's weight is given, or percentage weight is given. The person's total weight is given. No, okay, just deal with percentage weight. Then things will get cancelled anyways. So that is, weight will show up in numerator and denominator. Any common terms will get cancelled. So you don't have to worry about it. So x bar will be equal to xi wi by sigma w, right? Where x's are given over here. So quickly, just three parts. Let me do this. 17.3 into 10.6 plus 42.5 into 4.6 plus 45 into 1.7 divided by. So notice you can have a factor of W there, but it will get anyways cancelled. 10.6 plus 4.6 plus 1.7. What do you get for this? So quickly do what is y bar. So, these are in centimeters, so I suppose this is also in centimeter, 26.9 centimeter. And this should be, and so this should be, I suppose, 44 centimeters. Notice if you have to wrap a rubber band around these 3 points, okay, let's say there is a nail here, nail here, nail here. You have to wrap a rubber band. Okay. The CG should lie within that rubber band. Known as a convex hull. CG should be within that. Okay. Yeah. Yeah, this number should be technically between the triangle formed by these 3 points. Okay. Consider the arm shown in this figure. Elbow is this, flex to the right. Okay. Notice, okay, so here is one example where we did the entire free body diagram and solved it. Here they gave you the free body diagram, just solve for that. Suppose the values are not given here. So let's presume some distances and muscle tension and joint reaction force. We need to find Fj, Fm, and Fj and Fm. Right? I suppose W is W naught. Let's say all these are given. Let's do this symbolically. Okay. There are no forces in the x direction. So sigma fx is, not useful for us here at all. No, none of the forces in the x direction. Sigma fy is 0. Should get. Let's assume this to be positive. We have minus fj plus fm minus w. Yes, there is also w naught. So this should be 0. So there is one relation between fj and fm. Red right moment about O. Sigma moment about O is 0 for this thing to be equilibrium. So again, counterclockwise to be positive. So F times, Fm times, let's this distance, A, B, C. Technically, they should be given. So Fm times A minus W times B minus W times C is 0. So if A, B, C, W, W naught are given, we know Fm. Okay. So Fm is WB plus WC by A. And once we know that, we could also find F. Okay. Yeah, just plug this in here, you could find expression for Fy. But if we complete this symbolically, yeah, the space can be used for this. So Fy should be WB plus WC by A minus W minus W naught. So this is W naught. If the numbers are given, you can calculate what this Fy is. And they could also ask this in expression form. They don't have to ask things in numbers. So they can just give you expressions in variables and ask it. Okay. Now we get into the stress strain problem. In fact, the problems, the equilibrium problems, so we have seen so far are likely to show one other problem is this stress strain problem. So a cylindrical rod, a radius is given. With applying a force of Fs 1000 newtons, points A and B initially at a distance of 30 centimeters. After force is applied, they move by a distance of 31.5. What is the tensile strength and average tensile stress generated in the flow? Okay, this is tensile strain is change in length by original length, okay, L naught. And because it's a tension, length change is positive, okay, L minus L naught. L minus L naught is typically positive for tension. For compression, it will be negative. Tension, okay, so this is L minus L naught. Delta L should be 1.5. L naught is 30 centimeters. Both are in centimeters. Strain has no units. So what is this ratio? 0.05. Which is typically quite high for strain measure. Let's also quickly go ahead and find the average tensile stress. Sigma tension is just force per area. So force per area, force is 1000 newtons by area is, it's a cylindrical rod. So 3.14 into 1.26 square. This is in centimeter, so let's also do a 10 power minus 4 so that we get answer in Newton per meter square or in pascals. Okay. So what is this number over here? To MPa. I suppose, yeah, okay, fine. So we get 2 into 10 power 6 newtons per meter square. That is 2 into 10 power 6 pascals. Okay, that is 2 megapascals. Now it's the same problem. What they ask you to, okay, they ask you to do a couple of things. Experiment is design cortical tissue, 3 almost identical bone specimens. Okay, 3 specimens, square cross section. Okay, cross section area is given. 2 sections marked A and B or at a fixed distance apart. And before applying the force, we know the length. After applying a force, we know the length. Okay, you have to plot the stress strain curve. This is just to show that. Just show that how it's actually measured. So let's go ahead and do this. Determine the elastic modulus. Let's presume that all of them lie in a straight line. Okay, so some point like this. We'll likely have 3 points almost in this line. We have 0.1, 0.2, 0.3. Okay. So we have to find E from this. And this figure, interestingly, is L versus applied force. So we also have this point. When force is 0, this is 0. Then when force is 240, we have this length. Okay, so approximately just pick any one point, and the slope you can always find for this line. So pick any point. Let's just pick the center point. The slope here should be, we can technically get the slope from there, but that should not be directly the Young's modulus. The Young's modulus should be sigma by epsilon. Okay. That should be F over A into del L over L. Okay. And in fact, this should be del L so that we start at 0, 0. Now, so this slope that we have measured should be equal to EA by L, right? So this slope should be EA by L. That is, if you just plot these points, the slope here should be EA by L. Notice F is proportional to delta L. The proportionality constant is EA by L. But what in this case we want just this E. So let's just plug in the numbers from here and find it. So let's use one point, that is this, and quickly find out. So we have 480 into length is 5 mm initially. There is a delta L, so let's keep this in mm. Delta L and mm should be fine, they should get cancelled. Area, let's convert that into 2 square. So 2 square into 10 power minus 3 square, 10 power minus 6 meters. Wait, so right now this is in Newton per meter square. This delta L I'll write in mm. That delta L is 0.033. So this mm gets cancelled. Answer we get is in pascals. How many pascals here? Yeah. 480 into 5 divided 4 divided 10 power 6 divided 0.0. Yeah. What we get is 1.8 into 10 power 10, and this is 18 gigapascals. Steel would be like roughly 200, 500 gigapascals. We've also already seen this number kind of makes sense. And yeah, this detail is kind of, interesting. Now, if one were to, they could ask you, if one were to plot force versus change in length, what will be the slope of that curve? They can give you Young's modulus times EA, EA by L, and E by L, 4 options. Pick the correct option. Notice it should be EA by L. Okay. And of course, it comes from this basic relation. Okay. Okay, so this is some fun question. Let's number them. Okay, A, B, C, D, E, F, G, A, B, C, D, E, F, G, H. Yeah. So quickly. Okay, for A is 5. Okay, highest elastic modulus. Come on, how is A 5?
1.
Elastic modulus is this slope. 1. Okay, so 5 has the least elastic modulus. Okay, then let's go B, which is most ductile. This
5.
also, sorry?
5.
We have to be careful. What is ductility? How do we quantify ductility?
Sorry, it's 2.
See, 5 in fact is like a distractor. Okay, so 2. Notice the plastic strain in 2 is the highest. Okay, so starting from starts kind of yielding here, then goes till here. So plastic strain is highest in 2. This is 2. What is most brittle?
1.
Again, think about it.
4.
Yeah, we shouldn't be going by this. We should be going by plastic strain. Amount of plastic strain. So 4 is the most brittle. Okay. Yeah, this question, typically mistakes happen here. Okay, fine. Let's look at, if there are no questions, we'll look at D. Lowest yield strength. What is the top? Dot refers to yield point. The material starts yielding at that point. Okay, the stress corresponding to that is the yield stress. Cross corresponds to fraction. Yeah, in fact, it's written here, yield point and cross refers to rupture or fracture. Okay, now D, lowest yield strength is lowest yield strength. Yeah, where is the dot lowest here? It's perfect. Okay, and great. Next, material dash E, highest strength. And highest strength, they mean ultimate strength. Now we have lots of strength. If they don't refer to any other strength, it's the ultimate strength. 2 has the highest ultimate strength. Which is the toughest? Toughest material, yeah.
2.
2.
Okay, so toughest material, notice, has the highest area under the curve. The curve with the highest area under the entire strain curve is 2. Okay, and the material that is most resilient. Now we go to G. So what is it? 3.
3.
So resilience is the area under the elastic curve. Till yield point, the area should be the highest. Pretty much at the, the height is pretty much the same for the 2 triangles. Base is much higher for 3. So 3 certainly has is most resilient. Area under this elastic strain curve. That is measure of resilience. Finally, material is the most stiff, I suppose, is what is it? 1. Yeah, this is. Yeah, be careful about 2 things. Ductility and brittlity, always look for distance between this yield point and fracture point. And toughness and resilience, again, toughness area under entire curve, resilience area only till the first point. Okay, so we have some theory questions. Muscles are attached via aponeurosis or tendons to at least 2 bones, causing or controlling the dash of one bone with respect to the other. What word fits there? Like slightly wondering, motion or what? We have some kind of motion. Muscles are attached via neurosis or tendons to at least 2 bones, causing or controlling of one bone with respect to probably some motion. For example, if you had to take this, humerus, we have this bone over here, this bicep will connect there and connect here. Okay, as it contracts, this angle can be controlled. I just motion here. Okay, allows motion or movement, rotation, anything that is synonymous with that. Motion, movement, rotation, and typically bones allow rotation. Okay. Muscle exerts a dash effect on the bones to which it is attached. What does this thing do?
Pulling.
It pulling is word sounds odd. Can any other synonyms for pulling? Okay, this is like very simple. So just muscle tensile. Yeah, it pulls. Muscles have lower tensile strength as compared to. Yeah, this is simple, right? Bones.
Probably.
Bones would be. In fact, there is one more question. And just give me 1 second. So we have cartilage, ligament, tendon. Muscle should be, in fact, pretty much lesser than all of this. Okay, so pretty much anything would fit it. Bone. Even with respect to all the muscles become that one connecting point, right? Smaller area. So even bone tendon, the connecting part also it should be lower tensile. Okay. The primary function of cartilage is to facilitate dash of articulating bones. Again, the same synonym that would show up here: movement, motion, rotation of articulating bones. Okay, cartilage reduces dash applied to bones, and the dash of contact friction
Friction and reducing the contact.
Okay, applied to bones, increasing the lubrication of contact between the articulating cells. So this is friction, this is lubrication.
Yeah.
Friction and lubrication. No, but we also need the synovial joint and all. Any other words here? It doesn't say that synovial fluid, it specifically says the cartilage.
Is it the surface of contact?
Okay, so we have bones, and then on top of that, we have this cartilages. Okay. Had it been the synovial fluid, this would have been a better answer. For this, it has to do with more with the applied the pressure here. So it should be pressure or stress. Okay. In fact, instead of pressure, the better term here is stress, and it increases the area of contact. So this better word here again is area. Had it been synovial fluid, it's friction and lubrication. But for cartilage, then there is one more bone here. It is surrounded by this cartilage. And this is slightly of a higher area. The cartilage reduces bone wear by reducing the effect of dash between articulating surfaces.
This should be friction, I guess.
Friction.
Yeah, this is friction. You could also say reduces wear by reducing effect of is friction by reducing again stresses between articulating surfaces. Okay. If effect of is there, friction is better. During daily activities, the articular cartilage is subject to tensile and shear stress as well as dash stress. Should be compression, right? Yeah, there are only like tensile, shear, and then there is compression. So this thing can go either way, compression. And the best articular articulating cartilage will be intervertebral disc. So it's easy to imagine all three: tensile, shear, and compression. Okay. Some slightly weird fill in the blank questions. Okay, now we are headed to biofluids. Yeah, so questions we have already done, but let's also now quickly do this. One is for factors. So glomerulus filtration, total available area, resulting filtration radius. So this is in one pore, this is delta P by R. Okay, and quickly, what is R? 8 mu L by pi R. This is resistance. So what I have written is applied pressure is Q times resistance. So this is R naught power 4. This is correct, right? Resistance is this, right?
Yes, sir.
Okay. So in
Yes,
one
sir.
pore, this is how pressure, resistance, and flow are related. Now we have multiple pores in parallel. So total flow will be flow in one pore if all of them are same. Flow will be add all these flows. So if there are n pores, we will have n times q1. Okay. So Q1 it's simple, apply delta pressure. Okay, so this is delta P. In that, let's write this slightly in a more readable order. Total flow is, things are all, pores are all in parallel if you take that. So sum of all the force Q times N, Q1 times N. Q1 will be delta P by 8 mu L into pi R naught power 4. Number of pores, we can calculate one pore size, pores because we know the radius, and roughly we know the total pore area because it's given to be 5%. 5% of the total surface area of the membrane. So total area, membrane area is 1.5 meter square. So let me just, for now, A total by size of area of 1.5 R naught square. So this should give us the total flow, and we want the flow in centimeter cube per minute. So this is slightly involved, the calculation part. Okay, let's do that. Nothing necessary in the first thing. Okay, so the total flow should be delta P. Let's keep everything in SI to be safe. 1200 by 8 into viscosity. Viscosity 0.002 Pascal second. Length of one pore is 60 nanometer. So into 60 into 10 power minus 9. And we have some cancellations here. This becomes R square. This gets completely cancelled. So we have R naught square. Wow, 1 into 10 power minus 18 meter square times 80. That is 1.5 meter square, only 5% of that, 0.05. And all of this flow rate should be in meter cube per, where is the time coming from? Second. Because in pascals we have second, this entire thing should be in meter cube per second. Okay, can we quickly calculate what this value is? Then we'll have to convert that to centimeter cube per minute. Or let's also just introduce those numbers here. Let's not do some intermediate calculation. So per second, this much amount of flow. So per minute, it should be 60 more times. So here, let me do some unit corrections. So if we multiply by 60, this will be per minute. Okay, and these many meter cubes. How many centimeters cubes? 1 meter is 100 centimeter. So this will be 10 power 6 centimeter cube. 10 power 6. 1 centimeter is 10 power minus, 1 meter is 100 centimeters. So 1 meter cube is 100 cube, so 10 power 6 centimeter cube. So let's find this whole product. The answer should be in centimeter cube per minute. 8.43. Okay. Yeah. See, notice if they want to really pain you, they can take this simple thing. First of all, again, it's rephrased in this is a typical hard gate question. Hard gate question. Reason being, this is at analysis synthesis level. It's not directly this. You have to kind of realize you can apply this. Flow in one pore can be, if you know that, we can find the flow in all the pores. You have to do that synthesis. So analysis synthesis, it's very hard type of question. Okay, because initially you might be wondering, okay, how to, why is this radius given, this and all, oh sorry, why is this membrane area and all given, you might be wondering. That is at a slightly higher critical thinking. And then on top of that, they gave some nasty unit conversions. Meter cube per second to, you have to do centimeter cube per minute. Okay. So anyways, let's get to this thing. Yeah, few other ways they can play around with this. Poise is this. So before the exam, we'll make a list of all units. So you don't have to worry about it. At least, if you have notes of all units, share it with the group, or else even someone in the group, or I'll make a list of all units and we'll make it. Quickly, the Reynolds number in the renal artery. Okay, Reynolds number, we know how to find. It's rho v d by mu. Notice this d is the diameter. In Omersley number, the length scale is radius. Okay, so here you should use a diameter, there you should use the radius. So let's quickly also write down these things. Density of blood 1060. Mean velocity is 40 into 10 power minus 2 meter per second. And then diameter is 5 into 10 power minus 3 by mu. So one poise is 0.1 Pascal. So 3 centipoise is 0.3 into this is 1 poise 1 Pascal second. It should be viscosity, it should be Pascal seconds. And so this should be 0.3 into 10 power minus 2 Pascal second. So that is what we should be plugging in here. So velocity, there is a by second already there, so that should get cancelled. So what should we have here is 0.3 into 10 power minus 2 Pascal second. So the rest of the kilogram per meter cube Pascals should easily cancel. What do we get for this? Yeah, again, I note that hardly anyone got this correct because of this one damn thing. That is, what is poise? Roughly 706.7. Rounded off the nearest integer, 707. And also, for your memory, remember we have to use diameter and Reynolds number. If it is Umersley number, we have to use radius. In fact, I might have an example of that. Shear stress of on the wall of a renal arteriole is approximately. Were anyone able to find any data for that? But I think we did this in class, right? Were you able to find data for this? Okay, so how do we do this? This is simple, right? Tau is mu times gamma dot. We have to start with some relation. We have to know the shear rate or one of these things. Okay. This is 0.003, 0.005 Pascal second, 0.002 Pascal second. Anything will work here. Gamma dot is what we have to be careful about. This is velocity gradient. Velocity is velocity as a function of r is v naught into 1 minus r square by r square. the parabolic profile. So gamma dot is dou V by dou R. So that would be minus 2V naught R by R. Yeah, minus 2V naught R by R. Can you give me any mean velocity, maximum velocity, diameter, any of that? In fact, this is typically, so let's, if you look at the magnitude, the sign, just convention based on what you use for the convention, share it here. That's not of importance. So this can be in terms of average velocity. This will be V naught is 2V average R by R. Oh, come on. Why don't you just correct me? This is R square by R evaluated at the wall. So the R will get cancelled. We are evaluating this gradient at R is R. Control Z here today. See, this is evaluated at R is R. So if we have that, we just have this term. And then we have V over R roughly, and minus 8 VA by T. Either diameter, if you know average diameter velocity, you could easily find it. Anyways, let me go ahead and just give the expression for this. So tau should be equal to any of these times mu. So typically, let me have, say, this is a magnitude, 8 mu VA by D, okay? Or you could also say it's 4 mu VA by R, or you could also say this is 2 mu V naught by R. V naught is the maximum, VA is the average. Okay, so yeah, if you find values for this, I remember mu should be roughly 0.003 Pascal second. Okay, mean velocity and radius, if you plug in, you should get a reasonable value. Okay, let's go here. Whole blood is placed in concentric cylinder. Yeah, this problem we did in class. This is concentric cylinder viscometer. The same thing, right? Yeah, velocity gradient is this wall shear stress. So tau is mu times gamma dot. Gamma dot is gradient of velocity. So mu times R2 omega minus, say, omega 2 R1 omega 1 by H. And one of them will be 0. This omega will be 0. Right? So just product of these terms, let's just get the numbers correct. Okay, mu is going to be 0.0035 Newton per meter square second, Pascal second, fine. That times R2, radius of this wall will be 31 into 10 power minus 3. So that should be 0.031 times omega should be in radians. So 60 revolutions per minute. So it's 60 by 60 per second. Okay, revolutions 60 hertz. So into 2 pi radians. So all of this is 60 by 60 into 2 pi is omega in radians per second. And then your H is 0.00. Okay, quickly, so if you calculate this, what do you get? This should be in Newton per meter square. Zero point six eight two pascals. Fine. Okay. is application of differential manometer is connected to a tube to measure the pressure drop along the tube. And the directional reading is this. Okay, this is just playing with pressures. Pressure velocity, we can try to relate that, but no changes in cross section and all that. Okay, just playing with pressure. Now, how do we do this?
Bernoulli's theorem.
No, Bernoulli's, that's so the cross section doesn't vary. So, and we don't know the velocities here and here. Let's quickly see. P plus rho g h plus half rho v square is constant. Velocity, let's say it's a constant. Okay. Because flow rate here should be equal to flow rate here. And then these two are at the same height. Bernoulli's theorem we cannot apply to connect this. Okay. If there is a change in velocities, we can look for a streamline, but this is not a problem for Bernoulli's theorem. This is just, we have to relate the pressures here. So hydrostatic pressure, remember this rho g h is the hydrostatic component of pressure, right? So that is the hydrostatic. In fact, let me be clear. We directly jump to dynamics, so we will not go statics. So this is rho g times h. That is, we have some fluid, the pressure at a depth, h below the surface is going to be rho times g times h, hydrostatic pressure. Now, in fact, you could also refer to this as the static pressure. Okay. The thing is, and we also know one more rule. The same line, so along the same line, horizontal line, pressure is one and the same. Okay. And it holds good as far as the fluid is connected. Doesn't mean if the tube is going this way, and all that. Pressure here should be same as the pressure here if this is horizontal. In fact, that's how siphons work, right? So pressure at all these points should be the same if the fluid is connected, say through a pipe. So we have to horizontal line pressure is same. We have to use those two results. Horizontal line P is same. PH is same. PH. Okay, so let's quickly do that. Your point to compare would be, at this level we have, starting with here and here we have the same fluid. So this pressure is equal to, we cannot really differentiate that. But let's compare at this level. Okay, start with pressure 1 here, pressure 2 here. Let's call this depth till this point as something. How do we call that? Let's call this as depth D. Okay. So P1 is, so if you use this as a reference, that is, for now I'm just going to call this as 0 or a reference. Pressure is always relative. Okay. So this is my reference. So then all this will be negative. So let's just use this line as the reference. And so notice here fluid is flowing. Because of that, there is a change in pressure between this point and this point. But here the fluid is static, okay, because the flow doesn't occur this way, just measures the pressure difference. So here the static pressures across this line should be the same. So let's find the pressure through this point, then let's find the pressure through this point. They should be one and the same, okay. You take P1, then you have a additional pressure of rho g d, okay. And this, now there is also a difference between what this fluid is and what this fluid is. So one is this is a liquid. Differential manometer is connected pressure between the 2 points. Okay, yeah. This, notice density of this fluid is higher. Okay, so I'm going to call this as fluid 1, 2 will be confusing. Let's call this is water. Okay, so rho water. So that is pressure until this point. Plus pressure here will be rho this head. So again rho W G H. So from here starting, I got this pressure, I add this pressure, I get pressure at this point. Any questions here? This hydrostatic.
So this ultimately boils down to Bernoulli, right? Because we are ultimately measuring that P1, that same equation, right? Because we are considering P plus rho G H is equal to constant.
You are saying, okay, the velocity is, okay, within this you are trying to apply Bernoulli.
Yes, sir.
That is fine. The only thing is we have to be careful about the difference between this pressure and this pressure. Right here, I am saying, okay, start with some pressure value. Okay, then there is height change, so the Bernoulli pressure changes. That's your argument. And there is no velocity. So velocity here, so here velocity here is 0, velocity here is 0. That doesn't account for any head at all. Right? Okay, fair. Fine. Yeah, you assume so. There is 0 velocity here. You could apply essentially a version of Bernoulli is this. Okay. Then in the RHS at this point, so starting with P2, we have the same thing, water till height D, and then this thick fluid, let's just call it as rho till height H, rho GH. So this is common, this is common. What we should get is the pressure difference, P1 minus P2, P1 minus P2 should be rho minus rho W into GH. So obviously, yeah, if there is higher pressure here, it kind of drives this point up. So what is this value? We know rho, we know rho W, G is 9.8, H is also given 6 mm. Quickly, what is this value? 58.8. We have about 5 more questions. Let's quickly go through them. Some of the questions we haven't seen. So now, see, okay, arterial blood. What is the total oxygen content in the arterial blood? Oxygen content. Oxygen will be in 2 places. One, it will be in hemoglobin. Then it will, part of it will be dissolved. Part of it in hemoglobin can be found using this data. Okay. Hemoglobin concentration is this. Of that, Oxygen carrying capacity is, per gram it will carry 1.34 ml, and its efficiency is 95%. So from this we can say what the bound oxygen content is. Okay, and some of that will be dissolved. If you apply a pressure, oxygen will kind of dissolve in the fluid, not bound to this hemoglobin. So that per mmHg, there is a solubility of 0.003 ml. So if it is 40 mmHg, this times 40 should give the ml per dl. So this is dissolved. Total will be bound plus dissolved. Okay, so the total they are asking for should be bound plus dissolved. Interestingly, if you just gave the bound, dissolved will be very, very small fraction. If you just wrote the bound, that wasn't within the gate range. Okay, so be careful about it. Let's quickly find out this value. So the bound will be 15 gram per dl into 1 gram will have 1.34 with a efficiency or saturation of 95. Okay, so this is the bound part. What does this quickly boil down to? And this should be in ml per dl. I'll come to why this is in ml per dl in a moment. And okay, what is this value? And also tell me this value. So the dissolved is in fact much simpler. Dissolved should be 0.003.
0.12.
0.003 into 40. And again, this has been ml per dl. Okay, thanks. So this is 19.095. What is this? This is
0.12.
0.12. So this number should be 19.2, I suppose. In fact, let's get it slightly 0.012, right? Okay, correct. Yeah, 19.212. If you just even gave 19.095, it wasn't within the limits. Okay, that's how cruel the answer key was. But that this point is to emphasize the difference. Part of it is dissolved, part of it is bound. Most of it is bound, a small fraction is dissolved. And why this ml per dl? Can anyone answer that? And notice they want the answer in percentage volume by volume. And for that, some reason, if you give answer in ml per dl, we have things in, we have the correct answer. Why is that? Just 1 or 2 minutes here. So, okay, let's have both of them in common units. So ml per dl, how many ml is 1 dl? Deciliter. See, 10 power minus 3, 10 power minus 2, 10 power minus 1, 1. Right? And we have milli, centi, and deci. So how many ml is 1 dl? No, deci will be.
Sir, 1 deciliter is equal to 0.1 liter.
0.1 liter. I want in terms of, okay, that is how many ml is that? How many ml is 1.1 liter?
$10,000.
No, just be careful. In fact, yeah, see, Akansha said 1 ml is 0.01 deciliter. So 1 deciliter is 100 ml. Even Bonu said it's 100. Okay, so this is, notice 100 milli. So 100 times this you should, no, not 100 times this. This has like 100 milliwatts. Okay. So 1 dl is 100 ml. And does make sense, right? 100 times if you combine this, you get a part of that. Like 100 times centiliter will give you 1 liter. Like that, 100 small mLs will give you 1 deciliter. All of you agree with it? So what is given here is ml per dl is actually ml per 100 ml. That is, if you take 100 ml, with what ml of that is oxygen content. And because it's per 100 ml, the ml you get essentially is a percentage. So this units that we get answers in is in ml per 100 ml. So for 100 ml of the blood, you will have this many amount of ml of oxygen. So that directly is in terms of percentage. So in fact, this corresponds to percentage volume by volume. Okay. A few other questions I'll quickly brush through. Okay. Because we need to know a couple of things here. Hematocrit is percentage of RBCs. There are in 1 cubic milliliter, we have like 5 million RBCs. Okay. MCV is mean corpuscular volume, or roughly like what is the radius of an what is the volume of an RBC? Mean cell volume or mean corpuscular volume. You take 1 RBC, okay, the volume of that. So 1 MCV into, you multiply the number of RBCs, okay, in 1 cubic milliliter. So that is 5 into 10 power 6. Million is 10 power 6, right? So million is 10 power 6. What should we get here? This is volume of 1 RBC, total number of RBC in 1 cubic milliliter. What should we get?
Total volume of RBCs.
Yeah, total volume of RBC. Okay, volume of RBC. So interestingly, volume of RBC in that we also know that from hematocrit. If it is like 1 cubic milliliter, it should be like 45% of that. So what is this volume from hematocrit? We know that to be 0.45 cubic milliliter. So this should be mmq. So from this we can calculate what is MC. So just volume of 1 cell times number of cells should give you that volume of all the cells in the given volume, that is hematocrit. Okay, so based on that, quickly, if you do this, we'll get some very, very big numbers, big or two small numbers. So MCV is in terms of micron cube. So yeah, this should be a slightly nasty number. Can we, okay, quickly, what is this number? .45 by 5 into 10 power 6 mm cube. Let's also convert that into, meters. So this is into 10 power minus 9 meter cube. Okay, what is this value? And we have to convert this into micron cube. That is 10 power 6. Okay, 90 into 10 power minus 18. Meter cube. So notice, so this is 10 power minus 6 into 10 power minus 6 into 10 power minus 6. So give 10 power minus 6 to each of the meters, we should get 90 micron cube. Okay, so the answer here is 90. Okay, there are a couple of more things here. Blood cell count, we'll come to that, but right now I just use a simple volume relation. Okay, tensile, fortunately, some of the problems we have done a lot. So gate BM 2020, gate BM 2020. Only thing is, remember we start with 60 is some a e power bt, and then perhaps 50 is a e power b. If we start with this kind of relation, a is not 100. Okay. This also we know. When let me quickly. Anyone remember the answer was 70 days? Just to. And then this is this thing we know. We need the shrinkage. That's easier to find. Shrinkage is delta L. In fact, negative of that technically alpha L delta T. They should give us shrinkage. And then we have the Young's modulus stress. Sigma should be E times epsilon T. Okay. So E times, there are some signs here, but okay, E times minus epsilon T, but we just need the stress. So it's fine. E times epsilon T is alpha delta T. Okay. So using this relation, this is shrinkage, and this is the stress. Answer isn't it one of these things, these four things? 90, I suppose 15.75. Yeah, thanks. Yeah, another easy question. So 20 becomes 18, 20 minus 18 by 20 into 100%. So that is 10%. Yeah, this we have done. At the end of the day, find Young's modulus, also known as, in this case, tensile modulus. So sigma by epsilon, what is actually given is force by area into del L by L. T, A, L, del L are given here. And the answer should be in this range. Boom. Okay. Person sitting. Oh, these are. Suppose we are close to function. Sitting, standing, hip extends. The ankle slightly goes this way. There is plantar. Yeah, there is plantar. Mild plantar flexion. If hip extends, flexion cannot happen. Knee extension. Okay, so this answer not occurring is this. PKA line, yeah, this we have done 100 times, man. There is hip extension, and then there is knee flexion. Oh, sorry, this is hip flexion, and this is knee flexion. This is 50 degrees, and this is 20 degrees. So this angle, if let's say just this is vertical, so this should be 30 degrees. So this distance should be 400 sine 50 degrees plus 400 sine 30. So 300 sine 30 degrees. 300 sine 30 degrees. Okay. Fine. So I think, okay, that comes to the end of 460. Anyone remember this? Maybe? Okay. Where are we? 456. Yeah, and also remember, rounded off the nearest integer, I think it accepted either 456 or 457. Fine. So this see, this is from the medical imaging side, very, very comprehensive, first thing. And from biomechanics side, it reasonably covers numericals, especially it covers very, very well. And going through this, you also know what kinds of gate questions has showed up, how similar they are, and all that. Okay, so this is a nice list to have, and you could help this for revision, and just by going through this, your confidence should be really boosted. Okay, that is one thing. Remember, we have lots of MCQs from NPTEL. To be on the safe side, go over them. Okay, specifically, we have three things. What is this? Biomaterials, couple of them, 1 and 2. Then we have HAP. Then we also have, in fact, medical imaging, and we have for biomechanics. Not for biofluids, even that you should be able to find, but we have at least for biomechanics we have. Okay, if you go through this list and pretty much not just understand that one question, but all the options in that question, you are extremely, extremely well covered. Okay, and as I already said, bioinstrumentation, I will make it very, very easy for you. This week you will get bioinstrumentation 1. Okay, bioinst 1. So no prior knowledge, pure biomedical things you'll get. Then the next month you will get bioinst 2. So this will be bioinstrumentation that requires core knowledge. So I'll pull up pretty much all basic foundational things from signals and systems, circuits, then pretty much all the standard things you need, amplifiers, signal conditioning, all of that. I'll give you that. With that, if you know the things that we have done so far, other than what listed here, anatomy, aptitude, and mathematics, you are in very, very, very good shape. Okay. So your confidence should be very high by now. That is what I am thinking. And of course, we'll also start checking that from the mock next month onwards. The confidence should be very high. So yeah, you should start feeling good at this point. We have certainly come to that stage. Okay. And we'll start evaluating performances, strategizing things and all that once we have the mock test results. And towards the end, of course, in the mock test, I'll add some questions from advanced questions that are purely from the other side, so that we also don't miss out on that. Okay, so that is a plan. And then, yeah, start feeling better. That's my only thing. In fact, I heard some of you were feeling slightly afraid of the paper and all that. That shouldn't be the case. Okay, so let's stop here. Okay, 8:12. Weekend, I think, well used. So I'll see you again on Monday. Okay, have a good one.
Thank you, sir.
Thank you, sir.
Welcome. Bye.
Thank you, sir.
Bye, Niran. Bye. The spatial frequency. So your field of view. Just writing while it's not so sure. Really shows it. Wait. Okay. See, field. Just give me one second. Very small. Alternate cable just in case. problem occurs. Okay, fine. So I hope this works. It doesn't work. Okay. Okay. Yeah, I think this technical issue is sorted.